Tonight on The Sleepy Scientist, we ray drifting gently across the cosmic ocean to explore one of humanity's most profound milestones, NASA's discovery of 6,000 worlds beyond our solar system. From the first tentative detections of distant planets to the revolutionary space telescopes that peer into alien skies, we'll journey through the peaceful science of exoplanet exploration and discover what these distant worlds reveal about our place in the universe. In the vast darkness that stretches between the stars, where light takes years to travel from one stellar beacon to another, astronomers have discovered something extraordinary: a multitude of worlds, orbiting distant suns, each one a testament to the creative power of cosmic evolution. These exoplanets, as we call them, represent one of the most remarkable discoveries in the history of science, transforming our understanding of planetary formation and raising profound questions about the possibility of life beyond our earthly home. The milestone of 6,000 confirmed exoplanets represents more than a simple number. It symbolizes humanity's expanding cosmic awareness and our growing appreciation for the incredible diversity of worlds that populate our galaxy. Each of these distant planets tells a story about the conditions under which worlds can form, the processes that shape their evolution, and the remarkable variety of environments that exist throughout the cosmos. Tonight, as we embark on this peaceful journey through the science of exoplanet discovery, we'll learn how astronomers have managed to detect worlds so distant that their light takes decades or centuries to reach us. We'll explore the ingenious methods that allow scientists to infer the presence of planets around other stars, from the subtle dimming of starlight as planets pass in front of their suns, to the gentle gravitational tugs that reveal hidden worlds in the darkness. The search for exoplanets has revealed a universe far stranger and more wonderful than anyone could have imagined just a few decades ago. We've discovered planets made of diamond, worlds where it rains molten glass, and super-Earths that dwarf our home planet while orbiting closer to their stars than Mercury orbits our Sun. These discoveries have expanded our definition of what constitutes a planet and challenged our assumptions about the conditions necessary for world formation. As we prepare to explore this cosmic menagerie of worlds, we carry with us the knowledge that each discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? The growing census of exoplanets provides the foundation for this search, offering potential homes for life beyond Earth and helping us understand how common or rare our own world might be in the cosmic scheme of things. The story we'll tell tonight spans just over 3 decades of discovery, from the first confirmed exoplanet around a Sun-like star in 1995 to the sophisticated space-based surveys that now detect new worlds on an almost daily basis. This rapid acceleration in discovery represents not just technological progress, but a fundamental shift in our cosmic perspective from a universe centered on our solar system to one teeming with planetary possibilities. We'll meet the dedicated astronomers who have devoted their careers to this cosmic census, the engineers who built instruments sensitive enough to detect the faintest planetary signals, and the theorists who work to understand the complex processes that create and shape worlds throughout the galaxy. Their combined efforts have revealed a universe far more dynamic and diverse than previous generations could have imagined. As we begin this exploration, let us approach these distant worlds with wonder and humility, recognizing that each one represents a unique cosmic experiment in world building. In the gentle darkness between stars, planets form and evolve according to physical laws. We're still learning to understand creating environments that might harbor conditions suitable for life, as we know it, or perhaps forms of life we haven't yet learned to imagine. As we drift deeper into the story of humanity's greatest cosmic census, we must first journey back to the quiet revolution that began in the 1990s, when astronomers achieved something that had been dreamed of for centuries: the first confirmed detections of planets orbiting stars other than our Sun. This dawn of exoplanet discovery represents one of the most profound shifts in human understanding. Since Copernicus first suggested that Earth orbits the Sun, rather than standing at the center of creation. For most of human history, our solar system was the only known example of planets in the universe. While philosophers and scientists had long speculated about the possibility of other worlds, Detecting them remained beyond the reach of available technology. Planets, after all, are small and dim compared to the brilliant stars they orbit, making them extraordinarily difficult to observe directly. Across the vast distances of interstellar space, the breakthrough came not through direct observation, but through the detection of subtle gravitational influences that planets exert on their parent stars. As a planet orbits its star, it causes the star to wobble slightly, a motion so small that it requires extraordinary precision to detect. This technique, known as the radial velocity method, measures the periodic changes in a star's motion toward and away from Earth by analyzing tiny shifts in the star's spectral lines. The first confirmed exoplanet around a Sun-like star was discovered in 1995 by Swiss astronomers Michel Mayer and Didier Queloz, who detected the gravitational influence of a planet orbiting the star 51 Pegasi, located about 50 light-years from Earth. This discovery, which would later earn them the Nobel Prize in Physics, opened the floodgates for what would become one of the most productive periods of discovery in astronomical history. The planet orbiting 51 Pegasi, designated 51 Pegasi b, proved to be unlike anything in our solar system, with a mass comparable to Jupiter but orbiting its star in just over 4 days. Closer than Mercury orbits our Sun, this world challenged existing theories about planetary formation and migration. The discovery of this hot Jupiter forced astronomers to expand their understanding of how planetary systems could evolve and exist. Following this groundbreaking detection, astronomers around the world began developing increasingly sensitive instruments and techniques for finding exoplanets. The radial velocity method proved remarkably productive, revealing dozens and then hundreds of worlds orbiting nearby stars. Each new discovery added to our understanding of planetary diversity and the processes that shape planetary system architecture. American astronomer Jeff Marcy and his colleagues made significant contributions to these early discoveries, developing improved radial velocity techniques and confirming many of the first exoplanets detected by other teams. Their work established the systematic approach to exoplanet detection that would enable the field to grow from isolated discoveries to comprehensive surveys of nearby stellar neighborhoods. The early years of exoplanet discovery revealed a surprising fact. Planetary systems appeared to be common around Sun-like stars, but they often looked very different from our own solar system. Many of the first exoplanets detected were gas giants orbiting very close to their stars, earning the nickname hot Jupiters. These worlds challenged theories about planetary formation that had been based solely on our solar system's architecture. As detection techniques improved, astronomers began finding planets in more diverse configurations. Some planets orbited binary star systems, experiencing the light of 2 suns like the fictional world of Tatooine from Star Wars. Others followed highly elliptical orbits that would create extreme seasonal variations. The diversity of these early discoveries hinted at the even greater variety that would be revealed as technology advanced. The development of precise radial velocity measurements required innovations in spectrograph design and data analysis techniques. Astronomers had to account for stellar activity, instrumental effects, and other sources of noise that could masquerade as planetary signals. The precision required to detect Earth-like planets around Sun-like stars pushed technology to its limits and demanded years of patient observation to confirm detections. During this pioneering era, astronomers also began developing alternative detection methods that would prove crucial for future discoveries. The transit method, which detects the slight dimming of starlight when a planet passes in front of its star, offered the potential to find smaller planets and learn about their physical properties. Gravitational microlensing provided a way to detect planets around distant stars throughout the galaxy. The first decade of exoplanet discovery established several important principles that continue to guide the field today. Planets appear to be common around stars of various types, but planetary system architectures show remarkable diversity. The process of planetary formation and evolution is more complex and varied than theories based solely on our solar system had suggested. The search for Earth-like worlds would require increasingly sophisticated instruments and techniques. By the mid-2000s, the radial velocity method had detected several hundred exoplanets, establishing a solid foundation for understanding planetary populations around nearby stars. However, this technique was biased toward detecting large planets in close orbits, the ones that create the largest gravitational effects on their parent stars. Finding smaller, more Earth-like planets would require new approaches and space-based observations. The early exoplanet hunters worked with ground-based telescopes, battling atmospheric turbulence and other observational challenges while pushing the limits of instrumental precision. Their dedication and perseverance during this formative period laid the groundwork for the space-based missions that would revolutionize exoplanet science and enable the detection of thousands of worlds throughout our galactic neighborhood. As we prepare to explore how this pioneering work led to today's census of 6,000 confirmed exoplanets, we carry with us an appreciation for the vision and dedication of those early exoplanet hunters. Their patient work, measuring tiny stellar wobbles and analyzing subtle spectral shifts, opened our eyes to a universe filled with worlds we had only dreamed of finding. The dawn of exoplanet discovery marked the beginning of a new chapter in humanity's understanding of our place in the cosmos. Let us float gently toward the remarkable milestone that marks our current understanding of planetary abundance in the galaxy. The confirmation of 6,000 exoplanets, a cosmic census that represents one of the most extraordinary achievements in the history of astronomy. This number, tracked carefully by NASA's Exoplanet Science Institute, represents not just a count of distant worlds, but a transformation in our understanding of how common planetary systems are throughout the universe. The journey from the first confirmed exoplanet in 1995 to the 6,000th world detected today represents an acceleration of discovery that few scientists could have predicted. In the early years, each new planet was a significant event, often requiring years of observation and analysis to confirm. Today, space-based surveys detect new exoplanet candidates at a rate that sometimes exceeds one per day, though each still requires careful verification before joining the official census. NASA's Exoplanet Science Institute, based at Caltech's IPAC in Pasadena, California, serves as the keeper of this cosmic census, maintaining the official archive of confirmed exoplanets and coordinating the complex process of verification that transforms tentative detections into confirmed worlds. This archive represents the collective work of thousands of astronomers worldwide, each contributing observations, analysis, and insights to our growing understanding of planetary populations. The 6,000 confirmed exoplanets represent only a fraction of the known candidates, awaiting verification. More than 8,000 additional candidate planets have been detected but require follow-up observations to confirm their planetary nature and rule out false positives. This backlog of unconfirmed candidates suggests that the true census of detectable exoplanets may eventually reach tens of thousands or more as confirmation efforts continue. The acceleration of exoplanet discovery reflects both technological advances and the deployment of dedicated space-based missions designed specifically for planet hunting. Ground-based surveys, limited by atmospheric interference and other observational challenges, have given way to space telescopes that can monitor thousands of stars simultaneously with unprecedented precision and stability. These missions have transformed exoplanet science from a specialized field to one of the most active areas of astronomical research. Each confirmed exoplanet in the census represents a unique world with its own characteristics and evolutionary history. The diversity revealed by these 6,000 worlds has exceeded all expectations, showcasing planetary types that don't exist in our solar system and challenging theoretical understanding of planetary formation and evolution. From super-Earths larger than our home planet to mini-Neptunes smaller than Uranus, the exoplanet zoo displays remarkable variety. The census reveals that rocky planets appear to be more common throughout the galaxy than the gas giants that dominate our outer solar system. This finding has important implications for understanding planetary formation processes and for estimating the potential habitability of exoplanets. Rocky worlds, similar in composition to Earth, Mars, and Venus, may be more likely to support the conditions necessary for life as we understand it. The geographic distribution of these 6,000 worlds spans our local galactic neighborhood, with most detections concentrated within a few thousand light-years of Earth. However, some exoplanets have been found at distances approaching the galactic center, demonstrating that planetary formation occurs throughout the galaxy. The techniques used for detection determine how far astronomers can probe, with different methods sensitive to different distance ranges. Statistical analysis of the exoplanet census has revealed important insights about planetary system architecture and the frequency of different planet types. The data suggests that most Sun-like stars host at least one planet, and many systems contain multiple worlds. This finding implies that planetary formation is a natural and common outcome of star formation processes, rather than a rare accident that produced our solar system. The census has also revealed the existence of planetary system architectures that have no analog in our solar system. Some systems contain chains of planets locked in orbital resonances, creating complex gravitational relationships that maintain stability over billions of years. Others show evidence of violent evolutionary histories, with planets scattered into unusual orbits by gravitational interactions or stellar encounters. Perhaps most intriguingly, the census includes a growing number of planets located in the habitable zones of their stars, the regions where liquid water could potentially exist on planetary surfaces. While the presence of a planet in the habitable zone doesn't guarantee habitability, these worlds represent the best current targets for searching for signs of life beyond our solar system. The confirmation process that adds planets to the official census requires rigorous standards of evidence and often involves multiple independent observations. False positives can arise from stellar activity, instrumental effects, or other astrophysical phenomena that mimic planetary signals. The careful verification process ensures that the 6,000 confirmed exoplanets represent genuine detections rather than observational artifacts. International collaboration has been essential to building this cosmic census. Space agencies from around the world have contributed missions, observations, and expertise to the global effort to catalog exoplanets. Ground-based observatories on every continent participate in follow-up observations and confirmation campaigns. This cooperative approach has accelerated discovery and improved the quality of the resulting database. The impact of reaching 6,000 confirmed exoplanets extends beyond astronomy into broader questions about life, intelligence, and humanity's place in the universe. Each new world added to the census expands the potential locations where life might exist and increases the statistical likelihood that we are not alone. This growing inventory of worlds provides the foundation for future missions, designed to search for biosignatures and signs of life. The milestone also highlights the rapid evolution of astronomical capabilities. Over just a few decades, technologies that enable the detection of Earth-like planets around Sun-like stars were barely conceivable when the first exoplanet was discovered. The acceleration from dozens to thousands of known worlds demonstrates humanity's growing technological sophistication and our expanding ability to explore the cosmos, looking toward the future. The current census of 6,000 worlds represents just the beginning of exoplanet exploration. Next-generation space telescopes and detection techniques promise to reveal tens of thousands of additional worlds, including Earth-sized planets in the habitable zones of nearby stars. The James Webb Space Telescope has already begun analyzing the atmospheres of some known exoplanets, opening new windows into the nature of these distant worlds. The census also serves practical purposes for planning future exploration missions. Understanding the types and frequencies of different exoplanets helps mission designers optimize their instruments and observing strategies. The statistical properties of the known population guide target selection for atmospheric characterization and biosignature searches. As we continue our journey through the science of exoplanet discovery, we carry with us the profound significance of this cosmic census. The 6,000 confirmed worlds represent humanity's first comprehensive look at planetary populations beyond our solar system, revealing a universe rich with worlds and possibilities we are only beginning to understand. Each planet in this census tells a story about cosmic evolution and brings us one step closer to answering whether we are alone among the stars. Our peaceful journey now takes us to explore the ingenious techniques that have enabled astronomers to detect worlds so distant that their light takes years or decades to reach us. Finding exoplanets represents one of the most challenging tasks in observational astronomy, requiring extraordinary precision and innovative methods to tease planetary signals from the overwhelming brightness of their parent stars. These detection techniques have evolved into a sophisticated toolkit that reveals different aspects of distant worlds. The fundamental challenge of exoplanet detection lies in the vast difference between the brightness of stars and their orbiting planets. A typical star outshines its planets by factors of millions or billions, making direct observation extremely difficult. Imagine trying to see a firefly buzzing around a powerful searchlight from hundreds of miles away. This analogy barely captures the observational challenge that astronomers face when searching for exoplanets. The radial velocity method, which enabled the first exoplanet discoveries, works by detecting the gravitational influence that orbiting planets exert on their parent stars. As a planet orbits, it causes its star to wobble slightly, moving toward and away from Earth in a periodic pattern. This motion creates tiny Doppler shifts in the star's light that can be measured with extremely precise spectrographs, revealing the presence of unseen planetary companions. The precision required for radial velocity detection is extraordinary, measuring stellar motions as small as 1 meter per second, slower than a walking pace. Detecting an Earth-like planet around a Sun-like star requires measuring velocity changes of just centimeters per second, pushing instrumental capabilities to their absolute limits. This technique is most sensitive to massive planets in close orbits, as these create the largest gravitational effects on their stars. The transit method has proven to be the most productive technique for exoplanet discovery, responsible for detecting the majority of the 6,000 confirmed worlds. This method works by monitoring stars for periodic dimming events that occur when planets pass in front of their stars as seen from Earth. These mini-eclipses create tiny but measurable decreases in stellar brightness that reveal both the presence and some properties of the transiting planets. Transit observations can provide remarkably detailed information about exoplanets. The depth of the dimming event reveals the planet's size relative to its star, while the duration of the transit indicates the planet's orbital period and distance from its star. Multiple transits allow astronomers to determine precise orbital characteristics and even detect additional planets in the same system through their gravitational influences. However, the transit method requires a fortunate alignment between Earth, the exoplanet, and its star. Only a small fraction of planetary systems are oriented in a way that produces observable transits. From our perspective, despite this geometric limitation, space-based transit surveys have proven extraordinarily successful by monitoring hundreds of thousands of stars simultaneously, increasing the probability of detecting these rare alignment events. Direct imaging represents the most straightforward conceptual approach to exoplanet detection, simply taking a picture of the planet itself. However, this method faces enormous technical challenges due to the extreme brightness contrast between stars and planets. Current technology has succeeded in directly imaging fewer than 100 exoplanets, typically young, massive planets orbiting far from their stars where the brightness contrast is most favorable. The direct imaging technique requires sophisticated instruments called coronagraphs that can block the light from the central star while preserving light from nearby planetary companions. These instruments must suppress starlight by factors of billions while maintaining the sensitivity to detect the faint infrared glow of warm planets. Adaptive optic systems correct for atmospheric turbulence, enabling ground-based telescopes to achieve the angular resolution necessary for direct detection. Gravitational microlensing exploits Einstein's theory of general relativity to detect exoplanets around distant stars throughout the galaxy. When a star passes in front of a more distant background star, its gravitational field acts as a lens, magnifying the background star's light. Planets orbiting the foreground lens star can create additional magnification effects that reveal their presence even for Earth-mass planets around stars thousands of light-years away. Microlensing events are unpredictable and non-repeating, making this technique challenging but uniquely sensitive to planets at large orbital distances, where other methods lose sensitivity. The technique has revealed planets in the outer regions of planetary systems and provided important insights into the frequency of planetary systems throughout the galaxy. However, microlensing detections typically cannot be followed up with additional observations due to the transient nature of the lensing events. Astrometry, the precise measurement of stellar positions and motions, offers another approach to exoplanet detection by measuring the tiny orbital motion of stars caused by their planetary companions. This technique requires extraordinarily precise position measurements, detecting stellar motions smaller than the apparent width of a human hair, seen from several miles away. Space-based astrometric missions like the European Space Agency's Gaia satellite are beginning to detect massive planets through this method. The timing method has proven successful for detecting planets around pulsars rapidly rotating neutron stars that emit regular pulses of radiation. Planets orbiting pulsars cause tiny variations in pulse arrival times that can be measured with extraordinary precision. While pulsar planets are unlikely to be habitable due to the extreme radiation environment, these were actually the first confirmed exoplanets ever detected, discovered in the early 1990s before the first planets around normal stars. Each detection method has its own strengths and limitations, creating complementary capabilities when used together. Radial velocity measurements can confirm the planetary nature of transit candidates and determine planetary masses. Transit observations of radially detected planets can reveal planetary radii and atmospheric properties. Direct imaging can study the thermal properties and atmospheric composition of young, hot planets. The combination of multiple detection methods has proven essential for comprehensive characterization of exoplanet populations. Statistical studies require large samples of planets detected by consistent methods, while detailed studies of individual worlds benefit from multiple independent measurements. The diversity of available techniques has enabled the rapid growth in confirmed exoplanets and improved understanding of planetary system architecture. Technological advances continue to improve the sensitivity and capabilities of all detection methods. New instruments push precision to ever greater levels, while improved data analysis techniques extract more information from existing observations. The synergy between technological development and scientific innovation drives the ongoing acceleration of exoplanet discovery and characterization. Future detection methods may include techniques not yet fully developed, such as radio emission detection from exoplanet magnetospheres, or reflected light variations from planetary atmospheres and surfaces. The field of exoplanet detection continues to evolve rapidly, driven by the scientific goal of finding and characterizing Earth-like worlds that might harbor life. As we continue our exploration of the exoplanet census, we carry with us an appreciation for the ingenuity and precision required to detect these distant worlds. Each of the 6,000 confirmed exoplanets represents a triumph of observational astronomy and technological innovation, revealing worlds that exist in the darkness between stars, waiting for humanity's increasingly sophisticated tools to bring them into the light of scientific understanding. As we drift deeper into understanding how astronomers have catalogued 6,000 distant worlds, we encounter the most successful technique for exoplanet detection, the transit method, which has revealed the majority of known exoplanets by detecting the gentle shadows cast when planets pass in front of their stars. This elegant technique transforms one of nature's most subtle phenomena into a powerful tool for discovering and characterizing worlds throughout our galactic neighborhood. The transit method works on a beautifully simple principle. When a planet passes directly between T star and Earth, it blocks a tiny fraction of the star's light, creating a measurable dimming event that reveals the planet's presence. These planetary eclipses or transits typically reduce stellar brightness by less than 1%, a change so subtle that detecting it requires extraordinary precision and careful attention to instrumental stability and stellar variability. The geometry required for observable transits creates both opportunities and limitations for this detection method. Only planetary systems viewed nearly edge-on from Earth's perspective will produce transits, meaning that the vast majority of exoplanets cannot be detected this way. However, This geometric constraint is offset by the method's ability to monitor thousands of stars simultaneously, dramatically increasing the probability of discovering the small fraction of systems favorably aligned for transit detection. When astronomers observe a transit event, the precise shape and depth of the dimming curve reveals remarkable details about the transiting planet. The maximum depth of the transit indicates the planet's size relative to its star. Larger planets block more light and create deeper dimming events. The duration of the transit, combined with knowledge of the star's properties, reveals the planet's orbital period and distance from its star. Multiple transit observations allow astronomers to determine precise orbital characteristics and detect subtle variations that reveal additional information about the planetary system. Variations in transit timing can indicate the presence of additional planets in the system, whose gravitational influences slightly accelerate or delay the transiting planet's orbital motion. These timing variations have led to the discovery of numerous multi-planet systems. The transit method has proven particularly effective for detecting small, rocky planets that would be difficult or impossible to find using other techniques. While the radial velocity method favors massive planets that create large gravitational effects, the transit method is sensitive to planets of all masses, as long as they are large enough to create detectable dimming events. This capability has been crucial for finding potentially habitable worlds similar in size to Earth. Space-based transit surveys have revolutionized exoplanet science by achieving the precision and stability necessary to detect Earth-sized planets around Sun-like stars. The Kepler Space Telescope, launched in 2009, was the first mission dedicated specifically to transit photometry, monitoring over 150,000 stars continuously for more than 4 years. Kepler's unprecedented precision enabled the detection of planets smaller than Earth and revealed the abundance of super-Earths and mini-Neptunes. The Transiting Exoplanet Survey satellite TESS, launched in 2018, has continued and expanded the space-based transit revolution. While Kepler focused on a single field of view to achieve maximum sensitivity for small planets, TESS surveys the entire sky to catalog bright, nearby stars with transiting planets. This all-sky approach has identified thousands of new exoplanet candidates and provided targets for detailed follow-up studies. Ground-based transit surveys have also contributed significantly to exoplanet discovery, particularly for detecting larger planets around nearby stars. Networks of small, automated telescopes can monitor thousands of stars nightly, identifying transit candidates that can be confirmed through more detailed observations. These ground-based efforts have discovered many of the first transiting exoplanets and continue to find new worlds, especially around smaller, dimmer stars. The confirmation of transit candidates requires careful analysis to distinguish genuine planetary transits from false positives that can mimic transit signals. Eclipsing binary stars, where two stars orbit each other, can create dimming events that resemble planetary transits. Contamination from background stars or instrumental effects can also produce false signals. Statistical validation techniques and follow-up observations help distinguish real planets from these imposters. Transit observations provide unique opportunities to study exoplanet atmospheres through transmission spectroscopy. When a planet transits its star, starlight passes through the planet's atmosphere before reaching Earth, carrying signatures of atmospheric gases that can be detected through precise spectroscopic analysis. This technique has revealed the atmospheric compositions of dozens of exoplanets, including the detection of water vapor, carbon dioxide, and other important atmospheric constituents. The timing and frequency of transits also reveal important information about planetary system dynamics and evolution. Planets in multiple planet systems can show transit timing variations caused by gravitational interactions, allowing astronomers to determine planetary masses and orbital eccentricities. Some planets show periodic changes in transit depth or timing that indicate precessing orbits or changing atmospheric conditions. Secondary eclipses, which occur when planets pass behind their stars, provide additional information about planetary properties. These occultations can reveal planetary temperatures and thermal properties by measuring the decrease in total system brightness. When the planet's thermal emission is blocked by the star, combined with primary transit observations. Secondary eclipses enable detailed studies of planetary energy budgets and atmospheric dynamics. The statistical power of transit surveys has enabled groundbreaking studies of exoplanet populations and planetary system architecture. Large samples of transiting planets reveal the frequency of different planet types, the distribution of planetary sizes and orbital periods, and correlations between planetary properties and stellar characteristics. These statistical studies provide crucial insights into planetary formation and evolution processes. Recent advances in transit methodology include the development of techniques for detecting very small planets around very small stars. Red dwarf stars, which are much smaller and dimmer than the Sun, create favorable conditions for detecting Earth-sized planets because the relative size of the planet compared to the star is larger, producing deeper and more easily detectable transits. Several potentially habitable Earth-sized planets have been discovered around nearby red dwarf stars. Using these techniques, the combination of transit observations with other detection methods has proven particularly powerful for comprehensive exoplanet characterization. Radial velocity follow-up of transiting planets can determine planetary masses, enabling calculations of bulk density and inferences about planetary composition. Direct imaging of transiting planets can provide information about atmospheric scattering properties and thermal emission. Future developments in transit methodology focus on improving precision and expanding sensitivity to smaller planets around Sun-like stars. Advanced data analysis techniques using machine learning and artificial intelligence help identify weak transit signals in noisy data. Improved understanding of stellar variability enables better discrimination between planetary signals and stellar activity. The transit method has fundamentally transformed our understanding of planetary systems and their diversity. By revealing thousands of worlds through their subtle shadows, this technique has shown that planets are common throughout the galaxy, and that planetary system architectures display remarkable variety. The continued refinement of transit detection and analysis methods promises to reveal even more about the nature and prevalence of worlds throughout our cosmic neighborhood. As we continue exploring the census of 6,000 exoplanets, we carry with us an appreciation for the elegant simplicity and profound power of the transit method. These gentle planetary shadows, detected across vast distances with extraordinary precision, have opened windows into alien worlds and brought us closer to understanding our place in a universe filled with planets, possibilities, and perhaps life itself. Let us float gently towards some of the most extraordinary discoveries emerging from our census of 6,000 exoplanets, worlds so strange and wonderful that they challenge our understanding of planetary formation and expand our conception of what constitutes a planet. These alien worlds, existing in conditions unimaginable in our own solar system, reveal the remarkable creativity of cosmic evolution and the vast range of environments that planets can create and sustain. Among the most surprising discoveries are the hot Jupiter's gas giant planets that orbit their stars closer than Mercury orbits our Sun, completing their years in just days rather than months or years. These massive worlds, with temperatures exceeding 1,000 degrees Celsius, challenge our understanding of planetary migration and evolution. The first exoplanet discovered around a Sun-like star, 51 Pegasi b, belongs to this exotic class of worlds that simply don't exist in our solar system. The existence of hot Jupiters forced astronomers to reconsider theories about planetary formation and migration. These massive planets likely formed much farther from their stars, in the cold outer regions where ice and gas could condense, then migrated inward through gravitational interactions with their nascent planetary disks. Understanding this migration process has become crucial for explaining the diversity of planetary system architectures observed throughout the galaxy. Super-Earths represent another category of worlds, completely absent from our solar system. Rocky planets larger than Earth but smaller than Neptune, typically ranging from 1 to 5 times Earth's radius. These worlds appear to be among the most common types of planets in the galaxy, yet we have no local example to study. Their compositions, atmospheres, and potential habitability remain active areas of research and speculation. The diversity of super-Earth properties suggests they may represent several distinct classes of worlds. Some may be scaled-up versions of Earth with thicker atmospheres and stronger surface gravity. Others might be ocean worlds with deep global oceans beneath thick atmospheric layers. Still others could be rocky cores surrounded by substantial hydrogen-helium atmospheres, creating hybrid worlds between terrestrial planets and gas giants. Mini-Neptunes, slightly larger than super-Earths but smaller than Neptune, add another layer to the complexity of planetary classification. These worlds likely possess thick atmospheres of hydrogen and helium surrounding rocky or icy cores, but their exact compositions and internal structures remain uncertain. The transition between super-Earths and mini-Neptunes represents one of the most important frontiers in understanding planetary evolution and atmospheric retention. Some of the most exotic exoplanets discovered orbit binary star systems, experiencing the gravitational influences and illumination of two stars. These worlds, reminiscent of the fictional planet Tatooine from Star Wars, face complex orbital dynamics and variable stellar heating that create unique environmental conditions. Some planets orbit close to one star in a binary pair, while others orbit both stars at greater distances, experiencing dramatic changes in illumination and temperature. Perhaps even stranger are the free-floating planets worlds that have been ejected from their original planetary systems and now drift alone through interstellar space. Without any stellar illumination, these rogue planets, detected through gravitational microlensing events, challenge our definition of what constitutes a planet and suggest that planetary ejection may be a common outcome of planetary system evolution, particularly in systems with multiple massive planets. The census has revealed worlds with such extreme conditions that they seem more like science fiction than scientific fact. HD to 094558b, one of the first transiting hot Jupiters discovered, has temperatures so high that its atmosphere is literally evaporating into space, creating a comet-like tail of escaping material. This world provides a dramatic example of atmospheric escape processes that may be common among planets orbiting very close to their stars. Kepler 7b represents another extreme case of planet with the density of styrofoam, indicating a composition dominated by hydrogen and helium with very little solid material. This ultra-low density world challenges understanding of planetary formation and suggests that some gas giant planets may form through processes very different from those that created Jupiter and Saturn in our solar system. At the opposite extreme, some exoplanets appear to be composed primarily of carbon rather than the silicate rocks typical of terrestrial planets. These carbon planets or diamond worlds could have surfaces covered with graphite or diamond rather than silicate minerals, creating environments utterly unlike anything found on Earth or other planets in our solar system. While still theoretical, the possibility of such worlds expands our conception of planetary diversity. Lava worlds represent another extreme category, planets orbiting so close to their stars that their surfaces are molten rock. Kepler 7.8b, with an orbital period of just 8.5 hours, likely has a surface temperature exceeding 0 degrees Celsius, hot enough to melt rock and create global lava oceans. These worlds provide natural laboratories for studying planetary formation processes. Under extreme conditions, some exoplanets show evidence of highly elliptical orbits that create extreme seasonal variations. HD 80606b follows such an eccentric orbit that its surface temperature varies by more than 1,000 degrees during its 111-day year, ranging from relatively mild to hot enough to melt copper. These dramatic climate variations challenge our understanding of atmospheric dynamics and heat distribution on tidally heated worlds. The discovery of planets orbiting white dwarf stars, the burned-out remnants of sun-like stars, reveals that some worlds can survive the death of their parent stars. These planets have endured the violent red giant phase of stellar evolution, and now orbit in the dim twilight around stellar corpses. Their survival provides insights into planetary resilience and the long-term fate of planetary systems. Cloud composition on exoplanets adds another dimension to their strangeness. Some hot Jupiters likely have clouds made of vaporized metals, creating atmospheric conditions where iron and silicate particles condense out of the atmosphere. like exotic snow. Others may have clouds of sulfur compounds or other materials that would be toxic or corrosive under Earth conditions but represent normal weather patterns on their alien worlds. Tidally locked planets, where one hemisphere permanently faces the star while the other remains in eternal darkness, create extreme temperature gradients and unique atmospheric circulation patterns. These worlds may have day sides hot enough to vaporize rock, while their night sides remain cold enough to freeze atmospheric gases, creating dramatic weather systems as heat is transported between the hemispheres. The magnetic fields of exoplanets, while difficult to detect directly, likely create their own exotic phenomena. Hot Jupiters orbiting close to their stars may have magnetic field interactions that generate powerful radio emissions or create auroral displays far more spectacular than anything seen on Earth. These magnetic phenomena could potentially be detected with future radio telescopes, opening new windows into exoplanet characterization. Retrograde planets worlds that orbit their stars in the opposite direction from the star's rotation challenge conventional ideas about planetary system formation. These backwards worlds may have formed normally but been flipped into retrograde orbits through gravitational interactions with other planets or passing stars, providing evidence for the dynamic evolution of planetary systems over cosmic time. As we continue our exploration of the 6,000 world census, we carry with us a sense of wonder at the remarkable diversity and strangeness of these alien worlds. As we continue our exploration of the 6,000 world census, we carry with us a sense of wonder at the remarkable diversity and strangeness of these alien worlds. Each exotic exoplanet expands our understanding of planetary possibilities and reminds us that the universe is far more creative and varied than our solar system alone might suggest. These strange new worlds serve as natural laboratories for testing the limits of planetary formation and evolution, revealing processes and conditions that stretch the boundaries of our imagination and scientific understanding. Our peaceful journey now carries us to explore one of the most fundamental distinctions in planetary science: the difference between rocky worlds and gas giants, and what the census of 60 exoplanets has revealed about the relative abundance and characteristics of these two primary planetary types throughout our galaxy. This comparison provides crucial insights into planetary formation processes and helps us understand how common Earth-like worlds might be in the cosmic community of planets. In our own solar system, we see a clear division between the inner rocky planets Mercury, Venus, Earth, and Mars, and the outer gas giants Jupiter, Saturn, Uranus, and Neptune. This arrangement, with small, dense planets close to the Sun and large, gaseous worlds in the outer reaches, was long considered the standard template for planetary systems. However, the exoplanet census has revealed that this architecture is just one of many possible configurations and perhaps not even the most common. Rocky planets, also called terrestrial planets, are composed primarily of silicate rocks and metals, creating dense worlds with solid surfaces that can potentially support liquid water and the complex chemistry associated with life as we understand it. These worlds form through the gradual accretion of solid materials in the inner regions of planetary systems, where temperatures are high enough to prevent the condensation of water ice and other volatile compounds. Gas giants, in contrast, are composed primarily of hydrogen and helium surrounding small rocky or icy cores. These massive worlds form in the colder outer regions of planetary systems, where water ice and other compounds can condense to provide the solid foundation necessary for rapid gas accretion. The formation of gas giants requires a delicate balance of timing, material availability, and gravitational dynamics that may not occur in all planetary systems. One of the most surprising discoveries from the exoplanet census is that rocky planets appear to be far more common throughout the galaxy than gas giants. While our solar system contains equal numbers of rocky and gaseous worlds, surveys of exoplanet populations suggest that small, rocky planets outnumber gas giants by significant margins. This finding has important implications for understanding planetary formation efficiency and the potential prevalence of habitable worlds. The abundance of rocky planets becomes even more pronounced when considering the entire size distribution of exoplanets. The most common planetary size appears to be in the super-Earth range rocky worlds larger than Earth, but smaller than Neptune. These intermediate-sized planets don't exist in our solar system, but seem to be the most frequent outcome of planetary formation processes throughout the galaxy. Statistical analysis of Kepler mission data has revealed that roughly 50% of Sun-like stars host at least one planet larger than Earth but smaller than Neptune, while only about 10% host Jupiter-sized or larger planets. This size distribution suggests that the processes leading to rocky planet formation are more efficient or more common than those required for gas giant formation, at least for planets detectable by current survey methods. The distinction between rocky worlds and gas giants becomes less clear-cut when examining the full range of exoplanet properties. Super-Earths and mini-Neptunes occupy an intermediate zone where planets may have rocky cores, surrounded by substantial atmospheres of hydrogen and helium. The boundary between rocky with a thick atmosphere and small gas giant becomes increasingly blurred as we discover more worlds in this size range. Atmospheric retention plays a crucial role in determining whether a planet maintains its gaseous envelope or evolves into a bare rocky world. Planets orbiting close to their stars experience intense stellar radiation that can strip away atmospheric gases over time, potentially transforming mini-Neptunes into super-Earths. This atmospheric erosion process may explain some of the observed gaps in the size distribution of small exoplanets. The formation locations of rocky and gaseous worlds have been revolutionized by discoveries of planetary migration. Many of the gas giants detected in the exoplanet census orbit much closer to their stars than Jupiter or Saturn, suggesting that these worlds formed in the outer regions of their systems and then migrated inward. This migration process can dramatically alter planetary system architecture and the final distribution of different planet types. Compositional diversity within both rocky and gaseous categories adds complexity to planetary classification. Rocky planets may be dominated by different types of silicate minerals, metallic cores of varying sizes, or even exotic compositions like carbon-dominated worlds. Gas giants show similar diversity in their atmospheric compositions, cloud structures, and internal heat sources, creating subcategories within the broader classification scheme. The detection bias of different survey methods affects our understanding of the relative abundance of rocky and gaseous worlds. Transit surveys are sensitive to planets of all sizes, but favor those orbiting close to their stars, where transit probabilities are highest. Radial velocity surveys favor massive planets that create large gravitational effects. Direct imaging surveys can only detect young, hot gas giants that emit their own infrared light. Density measurements, obtained by combining transit and radial velocity observations, provide the most direct way to distinguish between rocky and gaseous compositions. The habitable zone plays different roles for rocky and gaseous worlds. Rocky planets in the habitable zone may support liquid water on their surfaces, creating conditions potentially suitable for life as we know it. Gas giants in the habitable zone cannot support surface life, but may host habitable moons with solid surfaces and subsurface oceans, expanding the definition of potentially habitable real estate. Atmospheric characterization reveals fundamental differences between rocky and gaseous worlds. Rocky planets may have thin atmospheres composed of gases released from their solid surfaces, or retained from their formation. Gas giants possess thick atmospheres that may extend to great depths, without clear boundaries between atmosphere and interior, creating complex layered structures with different compositions at different levels. The magnetic field generation mechanisms differ significantly between rocky and gaseous worlds. Rocky planets generate magnetic fields through dynamo processes in their metallic cores, while gas giants may generate fields through the motion of metallic hydrogen in their deep interiors. These different magnetic field structures affect how planets interact with stellar winds and cosmic radiation. Evolutionary pathways for rocky and gaseous worlds show both similarities and differences. Both types of planets can experience atmospheric loss, orbital migration, and tidal heating effects. However, the timescales and mechanisms of these processes vary significantly between dense rocky worlds and extended gaseous atmospheres, leading to different evolutionary outcomes over cosmic time. The search for life focuses primarily on rocky worlds due to their potential for surface conditions compatible with liquid water and complex chemistry. However, gas giants may also play important roles in supporting life by providing stable gravitational environments for potentially habitable moons or by protecting inner rocky planets from asteroid and comet impacts through their gravitational influence. Future missions and instruments will continue to refine our understanding of the rocky gaseous distinction and reveal new subtleties in planetary classification. The James Webb Space Telescope can analyze atmospheric compositions in unprecedented detail, while future direct imaging missions may reveal the prevalence of different planet types around nearby stars. Ground-based radial velocity surveys continue to improve their sensitivity to Earth-mass planets in habitable zone orbits. As we continue our exploration of the 6,000 world census, we carry with us an appreciation for both the fundamental similarities and crucial differences between rocky and gaseous worlds. The predominance of rocky planets in the galactic census suggests that the ingredients for potentially habitable worlds are common throughout the universe, while the diversity within both categories reminds us that planetary formation creates an endless variety of worlds, each with its own unique properties and evolutionary history. Let us drift gently into the realm of the most extreme worlds in our cosmic census, exoplanets that exist under conditions so harsh, unusual, or alien that they push the boundaries of our understanding of planetary science and challenge our concepts of what environments planets can create and sustain. These extreme worlds, scattered throughout the catalogue of 6,000 confirmed exoplanets, serve as natural laboratories for studying physics under conditions impossible to replicate on Earth. Among the most extreme exoplanets are those that orbit incredibly close to their stars, completing orbital periods in mere hours rather than days or years. WASP-1b represents one such world, orbiting so close to its star that it completes one orbit in just 26 hours, while experiencing surface temperatures exceeding 2,500 degrees Celsius. This scorching world is so hot that it's literally being torn apart by tidal forces, with material streaming from the planet toward its star in a process that will eventually destroy the planet entirely. The tidal destruction of WASP-1b creates one of the most dramatic planetary death scenarios known to science. The planet's atmosphere is being stripped away at a rate of about 10 billion tons per second, creating a comet-like tail of material that extends millions of kilometers behind the doomed world. This ongoing destruction provides astronomers with a real-time view of planetary disintegration and the extreme limits of planetary survival. At the opposite temperature extreme are planets orbiting at vast distances from their stars, or orbiting stars so dim that they receive virtually no stellar heating. These frozen worlds may have surface temperatures hundreds of degrees below freezing, creating environments where even the hardiest known life forms could not survive. Some of these cold worlds may still retain subsurface oceans beneath thick ice shells, similar to the moons Europa and Enceladus in our solar system. PSHB 1-57 plus 12b represents one of the most extreme planetary environments, known a world orbiting a pulsar, a rapidly spinning neutron star that emits intense beams of radiation. This planet, one of the first exoplanets ever discovered, experiences radiation levels millions of times higher than Earth, creating conditions that would sterilize any known form of life. The planet somehow survived the violent supernova explosion that created its neutron star parent, making it a testament to planetary resilience under extreme circumstances. Gravitational extremes create some of the most fascinating exoplanetary environments. Planets orbiting very close to massive stars experience gravitational fields so strong that they become tidally locked, with one hemisphere permanently facing the star while the other remains in eternal darkness. This creates temperature differences of thousands of degrees between day and night sides, driving extreme weather patterns and atmospheric circulation. HD 189733b showcases another type of extreme weather winds, reaching speeds of over 2,000 meters per second, or about 7 times the speed of sound on Earth. These supersonic winds are driven by the extreme temperature gradients between the planet's day and night sides, creating atmospheric circulation patterns far more violent than any weather system on Earth. The planet likely experiences storms that would make Earth's most powerful hurricanes seem like gentle breezes in comparison. Atmospheric composition extremes create worlds with skies and weather patterns unlike anything in our solar system. Some hot Jupiters have atmospheres where metals like iron and silicates exist as vapor, potentially creating clouds of liquid metal droplets and rain made of molten glass. HAT P7b appears to have clouds composed of corundum, the same mineral that forms rubies, and sapphires, creating a world where gemstones literally fall from the sky. Pressure extremes on gas giant exoplanets create conditions where familiar materials behave in exotic ways. In the deep interiors of massive gas giants, pressures may exceed those found at the center of Earth, crushing hydrogen into metallic states that don't exist anywhere in our solar system. These extreme pressures may create entirely new phases of matter and generate magnetic fields far stronger than any planetary magnetic field we know. Kepler 38b and similar worlds orbiting red dwarf stars face a different type of extreme environment-intense stellar flares that can temporarily increase their star's brightness by factors of 10 or more. These flares bombard the planet with high-energy radiation and charged particles, potentially stripping away any atmosphere and sterilizing the surface. The frequency and intensity of red dwarf flares create ongoing challenges for planetary habitability around the most common type of stars in the galaxy. Density extremes create worlds that challenge our understanding of planetary formation and evolution. Some exoplanets have densities lower than water, indicating compositions dominated by lightweight gases with little solid material. Others have densities exceeding that of iron, suggesting compositions dominated by heavy metals or exotic materials. These density variations reveal the remarkable range of conditions under which planets can form and the diverse outcomes of planetary evolution. Magnetic field extremes may create some of the most spectacular phenomena in exoplanet science. Hot Jupiters orbiting very close to their stars may generate magnetic fields thousands of times stronger than Earth's, creating auroral displays that could be visible from interstellar distances. The interaction between strong planetary magnetic fields and stellar winds may generate radio emissions detectable with future radio telescopes. Age extremes reveal worlds at different stages of planetary evolution. Some exoplanets orbit very young stars and may still be in the process of formation, with surfaces covered by molten rock and atmospheres filled with volcanic gases. Others orbit ancient stars billions of years older than our Sun, having experienced eons of evolution and potentially hosting highly evolved ecosystems, or the remnants of long-extinct civilizations. Orbital extremes create worlds with bizarre seasonal cycles and gravitational environments. Some exoplanets follow highly elliptical orbits that bring them alternately very close to and very far from their stars, creating extreme seasonal variations in temperature and radiation. Others orbit binary star systems with complex orbital dynamics that create unpredictable changes in illumination and gravitational forces. Size extremes span an enormous range from worlds smaller than Mercury to gas giants more massive than Jupiter. The smallest confirmed exoplanets approach the size of Earth's moon, while the most massive gas giants blur the boundary between planets and brown dwarf stars. This size diversity reflects the wide range of conditions under which planetary formation can occur, and the various evolutionary pathways that shape planetary development. Rotational extremes create worlds with days lasting anywhere from hours to months or even years. Some tidally locked planets have rotation periods equal to their orbital periods, creating permanent day and night hemispheres. Others may have been spun up by gravitational interactions to rotate extremely rapidly, creating oblate shapes and extreme centrifugal forces that affect atmospheric circulation and internal structure. Chemical extremes create worlds with surface compositions unlike anything in our solar system. Carbon planets may have surfaces covered with graphite or diamond rather than silicate rocks. Planets with high metal content may have surfaces dominated by iron, nickel, or other metallic elements. Water worlds may be entirely covered by global oceans thousands of kilometers deep, with no solid land surfaces whatsoever. Radiation extremes affect planetary evolution and potential habitability in complex ways. Planets orbiting active stars may be bombarded with X-rays and ultraviolet radiation that drives atmospheric chemistry and potentially strips away atmospheric gases. Conversely, planets around quiet stars may receive so little energy that they remain frozen throughout their existence, unless internal heating from radioactive decay or tidal forces provides alternative energy sources. These extreme exoplanets serve as crucial tests of planetary formation theories and atmospheric models. By studying worlds under conditions far beyond those found in our solar system, astronomers can test the limits of our understanding and discover new physical processes that operate under exotic conditions. Each extreme world teaches us something new about the remarkable diversity and resilience of planetary systems throughout the universe. As we continue our journey through the census of 6,000 worlds, we carry with us a sense of awe at the extreme conditions that planets can create and survive. These worlds remind us that the universe is far stranger and more varied than our Earth-centric perspective might suggest, and that the physical processes governing planetary formation and evolution can create environments that stretch the boundaries of our imagination and challenge our understanding of what constitutes a habitable or even survivable world. Our peaceful journey now takes us to perhaps the most profound aspect of exoplanet exploration, the search for worlds that might harbor the conditions necessary for life as we understand it. Among the 6,000 confirmed exoplanets, a growing number reside in the habitable zones of their stars, those precious regions where temperatures might allow liquid water to exist on planetary surfaces, and where the complex chemistry of life could potentially unfold. The concept of the habitable zone, sometimes called the Goldilocks zone, represents a range of orbital distances from a star where conditions are just right. For liquid water not too hot that water boils away, and not too cold that it freezes permanently. This zone varies in size and location depending on the star's temperature and brightness, with cooler stars having smaller, closer habitable zones and hotter stars having larger, more distant ones. However, the search for habitable worlds has revealed that planetary habitability involves far more than simple orbital distance. A planet's atmosphere, magnetic field, geological activity, and evolutionary history all play crucial roles in determining whether it can maintain conditions suitable for life. The discovery of potentially habitable exoplanets has therefore become an exercise in understanding the complex interplay of factors that create and maintain habitable environments. Kepler 4.5b, often called Earth's cousin, represents one of the most intriguing potentially habitable worlds discovered to date. This planet orbits a Sun-like star at a distance that places it squarely within the habitable zone, completing its year in 385 days, remarkably similar to Earth's orbital period. While we cannot yet determine whether Kepler 450b has an atmosphere or surface water, its size and orbital characteristics make it one of the most Earth-like worlds known. The TRAPPIST-1 system has captured scientific imagination as a laboratory for comparative habitability studies. This nearby system contains 7 Earth-sized planets, 3 of which orbit within the star's habitable zone. The proximity of this system, just 40 light-years from Earth, and the frequent transits of its planets make it an ideal target for atmospheric characterization studies using space-based telescopes. Like the James Webb Space Telescope, Proxima Centauri B holds special significance as the nearest known potentially habitable exoplanet, orbiting the closest star to our solar system at a distance of just 4.2 light-years. This world orbits within the habitable zone of its red dwarf star, though questions remain about whether it can maintain an atmosphere, given the intense stellar flares and radiation from its parent star. Future space missions may eventually be able to study this world in detail, making it humanity's first target for interstellar exploration. The prevalence of red dwarf stars, small, cool, long-lived stars that comprise about 75% of all stars in the galaxy, has focused much attention on habitability around these dim stellar objects. Red dwarfs have habitable zones much closer to the star, meaning that potentially habitable planets are likely tidally locked with permanent day and night hemispheres. This creates unique climate challenges. and opportunities that scientists are still working to understand. Atmospheric retention becomes a crucial factor for habitability around red dwarf stars. These stars emit intense ultraviolet radiation and produce powerful flares during their youth, potentially stripping away planetary atmospheres before stable climates can develop. However, red dwarfs also have lifespans measured in trillions of years, providing enormous timescales for life to evolve and develop if atmospheres can be maintained. The search for biosignatures, atmospheric gases, or other indicators that could reveal the presence of life represents the next frontier in habitability studies. Oxygen, ozone, methane, and other gases might indicate biological processes if detected in the right combinations and concentrations. However, distinguishing biological signatures from geological or atmospheric processes requires careful analysis and understanding of planetary atmospheric chemistry. Water vapor detection in exoplanet atmospheres has become one of the most sought-after measurements in the field. The James Webb Space Telescope has already detected water vapor in the atmospheres of several exoplanets, though most of these are hot gas giants unsuitable for life. Detecting water vapor around smaller, cooler planets in habitable zones remains a major goal for current and future observations. We're drifting gently across the cosmic ocean, where more than 6,000 distant worlds now shine in the light of human discovery, each one a testament to the patient persistence of our space-based observers. Imagine, if you were floating peacefully through the darkness between the stars, your consciousness expanding to encompass the vast network of robotic sentinels we have placed in space, our mechanical extensions reaching across the cosmos to peer at distant suns and catch the faintest whispers of worlds orbiting them. These space telescopes have become our cosmic eyes, opening vistas of discovery that have fundamentally transformed our understanding of our place in the universe. The story of exoplanet discovery is deeply intertwined with the story of human ingenuity and technological patience. For most of human history, the only planets we knew were the wandering stars visible to naked eyes: Mercury, Venus, Mars, Jupiter, and Saturn, along with our own Earth. The possibility that other stars might host planets remained pure speculation, a dream of philosophers and science fiction writers. But in the late 20th century, as our technology finally became sensitive enough to detect the subtle signs of distant worlds, everything changed. The first confirmed exoplanet around a Sun-like star, 51 Pegasi b, was discovered in 1995, and it immediately shattered our assumptions about how planetary systems form and evolve. Here was a world nearly as massive as Jupiter, but orbiting its star in just 4 days. A hot Jupiter that couldn't exist according to the theories of the time. This discovery opened the floodgates. Ground-based telescopes began finding more and more exoplanets using the radial velocity method, detecting the tiny gravitational wobbles that planets induce in their host stars. But the real revolution came when we lifted our search above Earth's atmosphere, deploying space telescopes specifically designed to hunt for distant worlds. With unprecedented precision and patience, the Kepler Space Telescope, launched in 2009, became our first dedicated exoplanet hunter in space. Named after Johannes Kepler, the 17th century astronomer who first described the laws of planetary motion. This mission employed a beautifully simple yet incredibly precise technique called transit photometry. Kepler would stare at a fixed field of stars for years, measuring the brightness of over 150,000 stars with extraordinary precision, waiting patiently for the telltale dimming that occurs when a planet passes in front of its host star. The transit method requires remarkable patience and precision. When an Earth-sized planet transits a Sun-like star, it blocks only about 0.008% of the star's light, a dimming so subtle that it would be like detecting the shadow of a coin held in front of a car's headlight from several miles away. Yet Kepler's instruments were so sensitive that they could detect these minute changes reliably, opening an entirely new window into the galaxy's population of planets. Kepler's discoveries transformed our understanding of planetary systems. During its primary mission from 2009 to 2013, and its extended K2 mission until 2018, Kepler discovered more than 2,600 confirmed exoplanets and identified thousands more candidates awaiting confirmation. The mission revealed that planets are incredibly common throughout the galaxy. Nearly every star hosts at least one planet, and many host multiple worlds in complex orbital arrangements. One of Kepler's most profound discoveries was the abundance of planets. Unlike anything in our own solar system, super-Earths, rocky planets larger than Earth, but smaller than Neptune, turned out to be among the most common types of planets in the galaxy. Despite being completely absent from our solar system, these worlds, with masses between 1.5 and 10 times that of Earth, occupy a middle ground between terrestrial and gas giant planets that we never knew existed, until Kepler showed us how common they are. Kepler also revealed the remarkable diversity of planetary systems. Some stars host planets orbiting closer than Mercury orbits our Sun, with surface temperatures hot enough to melt metal. Others harbor planets in complex chains of orbital resonances where multiple worlds dance in gravitational harmony, their orbital periods related by simple mathematical ratios. The mission discovered planets orbiting binary star systems, worlds that experience the light of two suns like the fictional Tatooine from Star Wars. The precision of Kepler's measurements also allowed astronomers to determine not just the sizes of exoplanets, but to begin characterizing their compositions and structures. By combining transit observations with radial velocity measurements from ground-based telescopes, scientists could determine both the radius and mass of distant planets, calculating their densities, and inferring whether they were rocky like Earth, gaseous like Jupiter, or something entirely different. As Kepler neared the end of its mission, NASA prepared its successor, the Transiting Exoplanet Survey Satellite, or TESS. Launched in 2018, TESS represents the next evolution in space-based planet hunting, designed to survey the entire sky rather than staring at one fixed field like Kepler. Where Kepler looked deep into space at relatively distant stars, TESS examines nearby stars, the stellar neighbors in our cosmic vicinity. TESS employs for wide-field cameras to monitor the brightness of over 100,000 stars, systematically surveying 85% of the sky over its 2-year primary mission. This all-sky approach means TESS can discover planets around the stars closest to Earth, making them ideal targets for follow-up observations with other telescopes, including the James Webb Space Telescope and future missions designed to study planetary atmospheres in detail. The strategy behind TESS reflects a sophisticated understanding of how exoplanet science has evolved. While Kepler proved that planets are common throughout the galaxy, TESS focuses on finding the specific planets that we can study in the greatest detail. A planet orbiting a nearby star is much brighter and easier to observe than one around a distant star, even if the distant planet might be more intrinsically interesting. Since beginning operations, TESS has been remarkably productive, discovering hundreds of new exoplanets and thousands of candidates. Among its discoveries are some of the most intriguing worlds found to date, including planets that might harbor liquid water, unusual multi-planet systems, and exotic worlds that challenge our understanding of planetary formation and evolution. One of TESS's most significant contributions has been the discovery of planets around nearby red dwarf stars. These small, cool stars are the most common type in the galaxy, and they have very long lifetimes. Some will burn for trillions of years, far longer than the current age of the universe. Red dwarf systems represent some of our best opportunities for finding potentially habitable worlds, and TESS has revealed that many of these nearby stars host planetary systems. The success of TESS has also demonstrated the value of international collaboration in exoplanet science. Ground-based telescopes around the world work in coordination with TESS, providing follow-up observations to confirm planet candidates and determine their masses and compositions. This global network of observers has dramatically accelerated the pace of exoplanet discovery and characterization. Beyond Kepler and TESS, numerous other space missions have contributed to our growing catalogue of exoplanets. The Spitzer Space Telescope, though primarily an infrared astronomy mission, made important contributions to exoplanet science by measuring the thermal emission from hot planets and studying the atmospheres of transiting worlds. The Hubble Space Telescope has provided some of the first detailed studies of exoplanet atmospheres, detecting water vapor, methane, and other molecules in the atmospheres of distant worlds. The European Space Agency's CHEOPS mission, launched in 2019, represents another approach to exoplanet studies. Rather than searching for new planets, CHEOPS focuses on characterizing already known worlds with extreme precision, measuring their sizes and studying their atmospheres. This detailed follow-up work is crucial for understanding the nature of the planets discovered by survey missions like TESS. Looking at ground-based contributions, the high-accuracy radial velocity planet searcher HARPS and similar instruments have been instrumental in measuring the masses of transiting planets discovered by space missions. These precise spectrographs can detect the tiny wobbles induced by planets with masses as small as Earth, providing crucial data about planetary compositions and structures. The synergy between space-based transit surveys and ground-based radial velocity measurements has proven incredibly powerful. Space telescopes excel at finding planets and measuring their sizes, while ground-based instruments determine their masses. Together, these measurements reveal planetary densities, allowing scientists to distinguish between rocky worlds, gas giants, and the mysterious intermediate category of sub-Neptune planets. The statistical power of our exoplanet surveys has also enabled new kinds of scientific studies. With thousands of planets discovered, astronomers can now study planetary populations statistically, looking for patterns and correlations that reveal how planetary systems form and evolve. These demographic studies have revealed that planetary system architecture is incredibly diverse. There is no such thing as a typical planetary system. One of the most important statistical findings from Kepler and TESS is the frequency of Earth-sized planets in the habitable zones of their stars. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where liquid water could exist on a planet's surface. Not too hot and not too cold, but just right. Estimates suggest that roughly 20 to 50% of Sun-like stars have Earth-sized planets in their habitable zones, implying billions of potentially habitable worlds in our galaxy alone. The precision of modern exoplanet detection has also enabled the discovery of remarkable planetary systems that seemed impossible just decades ago. Multi-planet systems where 5, 6, or even 7 planets orbit in complex gravitational dances. Planets orbiting extremely close to their stars with orbital periods of just hours. Worlds orbiting in the habitable zones of binary star systems. Planets around pulsars, the collapsed remnants of massive stars. Each new discovery has expanded our understanding of what's possible in planetary system formation. The hot Jupiters that were among the first exoplanets discovered forced astronomers to revise theories of giant planet formation and migration. The abundance of super-Earths revealed gaps in our understanding of terrestrial planet formation. The discovery of planets around binary stars showed that gravitational complexity doesn't preclude planetary formation. The data from these space-based surveys continues to yield new insights years after collection. Advanced analysis techniques, including machine learning algorithms, are being applied to Kepler and TESS data to find planets that were missed in initial searches. These second-pass discoveries often reveal smaller planets or those in more complex orbital configurations that require sophisticated analysis techniques to confirm. The legacy of missions like Kepler extends far beyond the planets they discovered directly. These missions proved that space-based photometry could achieve the precision necessary for exoplanet detection, validating techniques that will be used by future missions. They also demonstrated the value of long-duration, systematic surveys for understanding planetary populations on a galactic scale. As we drift through contemplation of these robotic observers and their remarkable discoveries, there is something profoundly moving about recognizing how they've fundamentally changed our perspective on our place in the cosmos. Before Kepler, we wondered whether planets like Earth might be rare and precious. Now we know that planets are common, and Earth-sized worlds in habitable zones number in the billions throughout our galaxy alone. The patient, systematic approach of these space telescopes, staring at stars for months and years, measuring tiny changes in brightness with incredible precision, mirrors the methodical nature of scientific discovery itself. Each photon of starlight carries information across vast distances and eons of time, and our instruments carefully collect and analyze this cosmic correspondence. to reveal the hidden worlds orbiting distant suns. These discoveries have also revealed the beautiful interconnectedness of astronomical phenomena. The same physical processes that formed our own solar system, gravity, accretion, migration, and evolution, have operated throughout the galaxy for billions of years, creating the diverse population of worlds we now know exists. Yet the outcomes of these processes are far more varied and surprising than we ever imagined, when we had only our own solar system as a guide. As we continue our gentle journey through the cosmos of exoplanet discovery, we can rest in the knowledge that our mechanical observers continue their patient work, adding new worlds to our catalogue with each passing day. TESS continues its systematic survey of nearby stars, while ground-based telescopes provide crucial follow-up observations. The data from past missions continues to yield new discoveries as analysis techniques improve, and our understanding deepens. The story of our cosmic eyes. These space telescopes that have opened the universe of exoplanets to our exploration reminds us that the most profound discoveries often require both advanced technology and patient persistence. Like astronomers carefully tracking the motion of planets across ancient skies, our modern planet hunters must wait and watch and measure with extraordinary precision, allowing the cosmos to reveal its secrets at its own pace. In contemplating these 6,000 worlds and counting, discovered through the patient gaze of our space-based observers, we find ourselves part of a much larger cosmic community than previous generations could have imagined. Each of these distant worlds represents possibilities and questions that will drive human curiosity for generations to come, while the techniques and technologies developed to find them continue to push the boundaries of what is possible in astronomical observation and discovery. As we continue our peaceful drift through the realm of exoplanet discovery, let us now turn our gentle attention to humanity's most sophisticated cosmic observatory, the James Webb Space Telescope, which has opened an entirely new chapter in our ability to study the atmospheres of distant worlds. There is something deeply moving about the way scientific discovery builds upon itself, each generation of instruments revealing new layers of cosmic complexity that were invisible to previous technologies. While Kepler and TESS showed us that planets are common throughout the galaxy, the James Webb Space Telescope has given us our first detailed glimpses into the atmospheric composition and chemistry of these distant worlds, transforming dots of light into complex dynamic environments with their own weather chemistry and perhaps even the potential for life. The James Webb Space Telescope represents one of humanity's greatest technological achievements. Webb's revolutionary capabilities for studying exoplanet atmospheres stem from its unprecedented sensitivity to infrared light. While our eyes see only visible light, Webb observes the universe in infrared wavelengths where molecules in planetary atmospheres leave their distinctive signatures. Water vapor, carbon dioxide, methane, ammonia, and countless other molecules each absorb specific wavelengths of infrared light, creating a unique spectroscopic fingerprint that Webb can detect and analyze. The technique Webb uses to study exoplanet atmospheres is elegantly simple in concept, yet incredibly sophisticated in execution. When a planet transits in front of its host star, some of the star's light passes through the thin shell of the planet's atmosphere. Before reaching us, the molecules in that atmosphere absorb specific wavelengths, creating tiny dips in the stellar spectrum that Webb can measure with extraordinary precision. These absorption features are incredibly subtle. We're talking about changes in starlight intensity of parts per million, variations so small they would be completely impossible to detect from Earth's surface due to atmospheric interference and thermal noise. Only a space-based infrared telescope with Webb's unprecedented stability and sensitivity can make such measurements reliably. Webb's first exoplanet atmospheric studies have already revolutionized our understanding of planetary atmospheres beyond our solar system. One of its earliest targets was WASP-96b, a hot Jupiter-type planet orbiting close to its star. Webb's observations revealed clear evidence for water vapor in the planet's atmosphere, along with evidence for clouds and hazes that affect how light passes through the atmospheric layers. The detail in Webb's atmospheric spectra is breathtaking when compared to previous observations. Where earlier instruments might detect one or two molecular features, Webb can simultaneously identify multiple atmospheric constituents and measure their abundances with unprecedented precision. These detailed spectroscopic analyses allow scientists to begin reconstructing the three-dimensional structure of exoplanet atmospheres, understanding how temperature and pressure vary with altitude, and how atmospheric chemistry changes throughout these alien worlds. One of Webb's most intriguing atmospheric studies focused on K-18b, a sub-Neptune planet orbiting in the habitable zone of a nearby red dwarf star. This world, about 2.6 times the radius of Earth, represents a type of planet that doesn't exist in our solar system, but appears to be common throughout the galaxy. Webb's observations detected water vapor and carbon dioxide in K-18b's atmosphere, along with a possible detection of dimethyl sulfide, a molecule that, on Earth, is only produced by living organisms. The potential biosignature detection around K-18b illustrates both the promise and the challenges of using Webb to search for life. Dimethyl sulfide is indeed produced by life on Earth, but confirming its presence in an exoplanet atmosphere and ruling out non-biological sources requires extremely careful analysis and independent confirmation. The detection represents a tantalizing hint of what might be possible. As Webb's observations continue and improve, Webb has also provided remarkable insights into the atmospheric dynamics of tidally locked planets, worlds, where one side always faces their star while the other side remains in permanent darkness. These planets, common around red dwarf stars, experience extreme temperature gradients that drive powerful atmospheric circulation patterns. Webb's ability to map temperature variations across planetary surfaces has revealed how heat is transported from day side to night side, providing crucial data for understanding atmospheric physics under conditions that don't exist anywhere in our solar system. The telescope's observations of WASP-18b revealed one of the most extreme planetary atmospheres studied to date. This ultra-hot Jupiter, with day-side temperatures exceeding 2,700 C, has an atmosphere where water molecules are completely dissociated into hydrogen and oxygen atoms. Webb detected the presence of water vapor on the cooler night side of the planet, showing how atmospheric chemistry can vary dramatically between different regions of the same world. Webb's atmospheric studies extend beyond individual planets to examine entire classes of worlds. By observing multiple hot Jupiters, Webb is revealing common patterns in atmospheric composition and structure that provide insights into how these planets form and evolve. Some hot Jupiters show evidence for high-altitude clouds and hazes that obscure deeper atmospheric layers, while others have clear atmospheres that allow Webb to probe deep into their chemical composition. The telescope has also begun studying smaller, more Earth-like planets, though these observations are more challenging due to the weaker atmospheric signals from smaller worlds. Webb's observations of rocky planets around nearby red dwarf stars are providing our first glimpses into the atmospheres of potentially habitable worlds, revealing whether these planets have managed to retain atmospheres despite the intense radiation from their host stars. One of Webb's most scientifically significant atmospheric studies examined planets in the TRAPPIST-1 system, a remarkable collection of 7 Earth-sized worlds orbiting an ultra-cool red dwarf star, just 40 light-years from Earth. Several of these planets orbit in the system's habitable zone, making them prime targets for atmospheric studies. Webb's initial observations of TRAPPIST-1b, the innermost planet, found no evidence for a substantial atmosphere, suggesting that the intense radiation from the star may have stripped away any atmosphere the planet once possessed. These null detections are as scientifically valuable as positive atmospheric discoveries. Understanding which planets retain atmospheres and which lose them provides crucial insights into planetary evolution and habitability. Red dwarf stars, which make up about 75% of all stars, are known to be magnetically active and to produce intense stellar flares that could strip atmospheres from nearby planets. Webb's observations are providing our first direct tests of how planetary atmospheres survive in these environments. The precision of Webb's atmospheric measurements has also enabled studies of atmospheric escape, the process by which planets lose their atmospheres to space over time. By measuring the abundances of different atmospheric constituents and comparing them to theoretical models, scientists can determine how planetary atmospheres have evolved over billions of years. These studies are crucial for understanding the long-term habitability of exoplanets and for predicting which worlds might maintain stable, life-supporting environments over geological timescales. Webb's atmospheric observations have revealed surprising diversity in exoplanet weather patterns. Some hot Jupiters show evidence for supersonic winds that transport heat from day side to night side with remarkable efficiency. Others appear to have more sluggish atmospheric circulation that allows extreme temperature gradients to persist. Cloud formation patterns vary dramatically between different worlds, with some planets showing clear skies while others are shrouded in thick, high-altitude hazes. The chemical diversity revealed by Webb's atmospheric studies has been particularly striking. While water vapor appears to be common in hot Jupiter atmospheres, the abundances vary significantly between different planets. Some worlds show evidence for carbon monoxide, others for hydrogen sulfide or various hydrocarbon molecules. These chemical differences provide insights into the formation histories of planets and the processes that have shaped their atmospheric evolution. Webb's ability to study atmospheric chemistry in detail has also revealed unexpected connections between planetary atmospheres and their formation environments. The carbon-to-oxygen ratio in planetary atmospheres, for example, provides clues about where in their stellar disk planets formed and how they migrated to their current orbits. Planets that formed closer to their stars show different chemical signatures than those that formed farther out and migrated inward later. The telescope's observations have also provided insights into atmospheric layering and vertical structure. By analyzing how atmospheric absorption features change with wavelength, scientists can determine how temperature and pressure vary with altitude in exoplanet atmospheres. These vertical profiles reveal the presence of temperature inversions, cloud layers, and other atmospheric phenomena that affect planetary climate and chemistry. One of the most exciting aspects of Webb's atmospheric studies is how they revealing the three-dimensional structure of exoplanet atmospheres. By observing planets at different phases, as they orbit around their stars and present different faces to our view, Webb can map how atmospheric properties vary across planetary surfaces. These phase curve observations provide unprecedented insights into atmospheric circulation patterns and the global climate systems of distant worlds. Webb's atmospheric measurements are also providing crucial calibration data for theoretical models of planetary atmospheres. Computer simulations of exoplanet climates must match Webb's detailed observations to be considered reliable, and discrepancies between observations and models are driving improvements in our understanding of atmospheric physics and chemistry. This iterative process between observation and theory is rapidly advancing our ability to predict and understand exoplanet atmospheric behavior. The implications of Webb's atmospheric discoveries extend far beyond individual planets to questions about habitability and the potential for life. By studying how different types of atmospheres behave under various stellar conditions, Webb is helping scientists understand which planetary environments might be most conducive to the development and persistence of life. These insights will be crucial for prioritizing targets for future missions. Designed to search for biosignatures more systematically, Webb's atmospheric studies are also revealing important connections between planetary and stellar properties. The composition and structure of planetary atmospheres appear to be influenced not just by planetary mass and orbit, but also by the age, activity level, and metallicity of host stars. These correlations provide insights into how planetary systems form and evolve as integrated systems, rather than collections of independent objects. The precision and detail of Webb's atmospheric observations have exceeded even the most optimistic predictions made before the telescope's launch. The quality of atmospheric spectra Webb can obtain in a single transit observation surpasses what previous instruments could achieve with dozens of observations. This unprecedented capability is enabling studies of atmospheric variability and chemistry that were simply impossible with earlier technology. As Webb continues its atmospheric studies, Scientists are developing increasingly sophisticated techniques for extracting maximum information from the telescope's observations. Machine learning algorithms are being applied to identify subtle spectroscopic features that might be missed by traditional analysis methods. Statistical techniques are being used to combine observations of multiple planets to study atmospheric populations and identify common patterns. The future of Webb's atmospheric studies looks remarkably promising. The telescope's instruments continue to perform flawlessly, and scientists are developing increasingly ambitious observational programs. Plans are underway to study the atmospheres of potentially habitable rocky planets, to search for biosignatures in nearby planetary systems, and to conduct systematic surveys of atmospheric composition across different types of worlds. In contemplating Webb's revolutionary atmospheric discoveries, we can find both wonder and humility. Wonder at the technological achievement that allows us to analyze the chemical composition of worlds orbiting other stars, and humility in recognizing how much we still have to learn about these distant atmospheric systems. Each new observation reveals unexpected complexity and diversity, reminding us that the universe continues to surprise us with phenomena beyond our current understanding. The gentle patience required for Webb's atmospheric studies, carefully pointing at distant stars, for hours at a time collecting photons that have traveled across interstellar space carrying information about alien atmospheres, reflects the broader rhythm of astronomical discovery. Like all profound scientific insights, understanding exoplanet atmospheres requires both advanced technology and the patience to let distant worlds reveal their secrets at their own pace. As we drift peacefully through contemplation of these atmospheric revelations, we can rest in the knowledge that Webb continues its observations night after night, gradually building our understanding of how planetary atmospheres work throughout the galaxy. Each new spectrum adds to our knowledge of atmospheric chemistry, dynamics, and evolution, bringing us closer to answering fundamental questions about habitability and our place among the worlds of the galaxy. As we continue our gentle journey through the expanding universe of exoplanet discovery, let us now drift forward in time to contemplate the next generation of space telescopes that will soon join our cosmic fleet, each designed to push the boundaries of what we can learn about distant worlds and our place among them. There is something deeply satisfying about the way space missions build upon each other, each generation learning from the successes and limitations of its predecessors, gradually developing more sophisticated capabilities for exploring the cosmos. While the James Webb Space Telescope has revolutionized our ability to study exoplanet atmospheres, the missions now under development will open entirely new avenues of discovery, employing techniques and technologies that were barely conceivable just a generation ago. The Nancy Grace Roman Space Telescope, scheduled to launch no later than May 2027, represents the next major step in NASA's exoplanet exploration program. Named after the pioneering astronomer who laid the groundwork for the Hubble Space Telescope, Roman will complement and extend the discoveries made by previous missions. Through a combination of unprecedented survey capability and revolutionary new detection techniques, Roman's primary mirror, at 2.4 meters in diameter, is identical to Hubble's, but the telescope's field of view will be more than 100 times larger than Hubble's, allowing it to observe vast areas of sky with remarkable efficiency. This wide field capability makes Roman ideally suited for large-scale surveys that can discover thousands of new exoplanets, while also studying the statistical properties of planetary populations throughout our galaxy. One of Roman's most exciting capabilities will be its systematic survey, using gravitational microlensing, a technique that can detect planets that would be impossible to find using transit or radial velocity methods. When a star passes directly in front of a more distant background star from our perspective, the foreground star's gravity acts as a cosmic magnifying glass, focusing and amplifying the light from the background star. If the foreground star has planets, they create additional magnification events that can be detected as brief brightenings in the background star's apparent brightness. Gravitational microlensing is particularly sensitive to planets at Earth-like distances from their stars, the orbital separations where liquid water could exist on planetary surfaces. unlike transit surveys, which are most sensitive to planets orbiting very close to their stars. Microlensing can detect planets throughout their stellar systems, including those in the habitable zones where life might develop. Roman's microlensing surveys expected to discover thousands of new planets, providing our first comprehensive census of planets at Earth-like orbital distances throughout the galaxy. The microlensing technique also has the remarkable ability to detect rogue planets, worlds, that have been ejected from their stellar systems and now wander through interstellar space without host stars. These orphaned worlds, if they exist in large numbers as some theories predict, could represent a significant population of planets that would be completely invisible to other detection methods. Roman's survey may reveal whether rogue planets are common or rare, providing important insights into planetary system formation and evolution. Beyond its survey capabilities, Roman will carry a technology demonstration instrument called the Roman coronagraph, which will attempt something that has never been achieved from space: directly imaging exoplanets by blocking out the light from their host stars. This coronagraph technology is incredibly challenging to implement. Imagine trying to see a firefly next to a searchlight from thousands of kilometers away, and you'll appreciate the technical difficulty of directly imaging exoplanets. The Roman coronagraph will use advanced optical techniques to suppress starlight by factors of billions, creating an artificial eclipse that allows the faint light from nearby exoplanets to be detected and studied. While this technology demonstration will only be able to image a few of the brightest, largest exoplanets around nearby stars, it will prove techniques that will be essential for future missions designed to search for Earth-like planets around Sun-like stars. Direct imaging represents the holy grail of exoplanet detection because it allows comprehensive study of planetary properties without requiring special geometric alignments or orbital motions. A directly imaged planet can be studied continuously, allowing astronomers to monitor changes in its atmosphere, search for moons or ring systems, and conduct detailed spectroscopic analysis of its atmospheric composition. The Roman coronagraph will provide crucial experience in space-based direct imaging techniques that will inform the design of more advanced future missions. The combination of Roman's wide field survey capabilities and direct imaging technology demonstrations positions it as a bridge between current exoplanet missions and the even more ambitious observatories planned for the 2030s and beyond. Roman's discoveries will identify the best targets for detailed follow-up study by future missions, while also providing the statistical foundation needed to understand how common different types of planetary systems are throughout the galaxy. Looking beyond Roman, NASA is developing plans for the Habitable Worlds Observatory, a mission concept that would be specifically designed to search for signs of life on Earth-like exoplanets around Sun-like stars. This future mission would employ advanced coronagraph technology to directly image potentially habitable planets and analyze their atmospheric composition for biosignatures, chemical indicators that could reveal the presence of life. The Habitable Worlds Observatory would need to achieve contrast ratios of 10 billion to 1 or better to detect Earth-like planets in the habitable zones of nearby Sun-like stars. This represents an enormous technological challenge that will require advances in optical systems, vibration control, and coronagraph design far beyond what is currently achievable. The mission would likely use a segmented primary mirror larger than Webb's, possibly deployable in space like Webb's mirror but optimized for visible and near-infrared observations rather than infrared astronomy. The scientific goals of the Habitable Worlds Observatory are breathtaking in their ambition. The mission would search for water vapor, oxygen, ozone, and other potential biosignatures in the atmospheres of dozens of nearby Earth-like planets. It would also search for surface features that might indicate the presence of continents, oceans, and seasonal changes that could provide additional evidence for habitability or even active biological processes. International collaboration will play crucial roles in future exoplanet missions. The European Space Agency is developing Plato planetary transits and oscillations of stars, a mission that will monitor hundreds of thousands of stars simultaneously to search for Earth-like planets around Sun-like stars using the transit method. Plato's unique approach will be to study stellar oscillations subtle vibrations in stellar surfaces to determine precise ages and properties of host stars, providing crucial context for understanding planetary system evolution. Plato's long-duration observations, planned to last at least for years with possible extensions, will be sensitive to planets with orbital periods up to several years, potentially detecting true Earth analogues orbiting in Earth-like orbits around Sun-like stars. This capability fills a crucial gap in current exoplanet surveys, which are most sensitive to planets with short orbital periods that transit frequently. China is also developing ambitious exoplanet missions, including the Earth 2.0 ET Space Telescope, planned for launch in 2028. This mission will conduct a 4-year survey searching for Earth-like planets around Sun-like stars, complementing international efforts to characterize the population of potentially habitable worlds in our cosmic neighborhood. The international nature of future exoplanet exploration reflects the global interest in answering fundamental questions about planetary systems and the potential for life beyond Earth. Advanced ground-based facilities will also play important roles in future exoplanet studies. The extremely large telescopes currently under construction, including the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope, will have collecting areas and angular resolution capabilities that surpass current space telescopes in many applications. These giant ground-based telescopes, equipped with advanced adaptive optics systems to compensate for atmospheric turbulence, will be able to directly image young exoplanets around nearby stars and conduct detailed spectroscopic studies of their atmospheres. The synergy between space-based and ground-based exoplanet observations will become increasingly important as the field matures. Space telescopes excel at systematic surveys and observations requiring extreme stability, while ground-based telescopes can provide high-resolution spectroscopy and rapid follow-up observations of interesting targets. The combination of these complementary capabilities will enable more comprehensive studies of exoplanet properties than either approach could achieve alone. Future exoplanet missions will also benefit from advances in artificial intelligence and machine learning techniques. The volume of data produced by next-generation surveys will far exceed what human astronomers can analyze manually, requiring automated systems to identify planet candidates, classify their properties, and prioritize targets for follow-up observations. Machine learning algorithms are already being applied to existing exoplanet data with remarkable success, and these techniques will become even more important as survey capabilities expand. The development of new detector technologies will also enable future missions to achieve unprecedented sensitivity and precision. Advanced infrared detectors with improved noise characteristics and larger formats will allow space telescopes to conduct more sensitive atmospheric studies of smaller, more Earth-like planets. New approaches to stellar coronagraphy, including star shades, large, specially shaped screens flown in formation with space telescopes to block starlight, may enable direct imaging of Earth-like exoplanets years before traditional coronagraph technology matures sufficiently. Looking even further into the future, concepts for truly revolutionary exoplanet missions are being studied. Interferometric arrays of multiple space telescopes flying in precise formation could achieve angular resolution equivalent to telescopes hundreds of meters in diameter, enabling detailed surface mapping of nearby exoplanets. Solar gravitational lensing missions could use our own sun as a cosmic magnifying glass to achieve extraordinary resolution for studying specific exoplanets, though such missions would require spacecraft to travel to distances of 550 astronomical units or more from the Sun. The progression from current missions to these future concepts illustrates the exponential growth in our capabilities for studying exoplanets. Each generation of missions enables discoveries that inform the design of subsequent missions, creating a positive feedback loop that accelerates the pace of discovery. The statistical surveys conducted by missions like Kepler and TESS identified the types of planets that are most common and most interesting for detailed study. Atmospheric studies by Webb are revealing which planets have atmospheres suitable for biosignature searches. Future missions will build on these foundations to search systematically for signs of life on the most promising targets. The technological challenges involved in future exoplanet missions are driving advances in numerous fields of engineering and physics. Precision pointing and vibration isolation systems developed for space-based coronagraphs will have applications in gravitational wave detection and quantum physics experiments. Advanced optical systems designed to suppress starlight will benefit astronomical observations more broadly. The computational techniques developed to analyze exoplanet data will find applications in medical imaging, materials science, and artificial intelligence. The international cooperation required for future exoplanet missions reflects the global nature of the questions being addressed. Understanding planetary system formation, the frequency of habitable worlds, and the potential for life beyond Earth are questions that transcend national boundaries and require the combined expertise and resources of the international scientific community. The collaborative approach to future exoplanet missions provides a model for how humanity can work together to address the most profound questions about our place in the universe. As we contemplate these future missions and their revolutionary capabilities, there's something deeply inspiring about humanity's commitment to understanding our cosmic environment. The technical challenges are enormous, the timescales are long, and the questions being addressed are among the most profound in all of science. Yet the steady progress from mission to mission, each building on the discoveries and techniques of its predecessors, demonstrates our species' remarkable persistence in pursuing knowledge and understanding. The gentle patience required for these long-term mission development efforts mirrors the patient observations required for exoplanet detection itself. Just as astronomers must wait months or years for planetary transits or gravitational microlensing events, the scientific community must wait years or decades for new missions to be developed, launched, and begin producing discoveries. This extended timeline reflects the inherent complexity of space missions and the careful engineering required to achieve unprecedented capabilities. In the harsh environment of space, future exoplanet missions will also benefit from lessons learned during the development and operation of current missions, where their successful deployment and operation have validated new approaches to space telescope design that will be applied to future missions. Roman's wide-field survey techniques will inform the design of even more ambitious survey missions. Each mission serves as both a discoverer of new worlds and a proving ground for technologies that will enable future discoveries. In contemplating this progression of increasingly capable exoplanet missions, we can find both excitement about future discoveries and appreciation for the remarkable achievements already accomplished. The transition from wondering whether exoplanets exist at all to planning missions that will search systematically for signs of life on distant worlds represents one of the most remarkable scientific and technological achievements in human history. As we drift peacefully through these contemplations of future capabilities and discoveries, we can rest in the knowledge that human curiosity and ingenuity continue to push the boundaries of what is possible in astronomical observation and discovery. The missions now in development will open new chapters in our understanding of planetary systems and our place among them, while also laying the groundwork for even more ambitious explorations that will extend humanity's reach deeper into the cosmos in the decades and centuries to come. As we continue our peaceful drift through the cosmos of discovery, let us now turn our contemplative attention to perhaps the most profound question that exoplanet science enables us to explore. Are we alone in this vast universe, and how might we recognize the signatures of life on distant worlds orbiting other stars? There is something deeply moving about the realization that, for the first time in human history, we possess the technological capability to search systematically for signs of life beyond Earth. This search represents the convergence of centuries of scientific progress, from the development of spectroscopy in the 19th century to the deployment of space telescopes capable of analyzing the atmospheric composition of planets orbiting other stars. The search for life on exoplanets begins with understanding what we mean by life and how living processes might leave detectable signatures in planetary atmospheres or surface features. On Earth, life has profoundly altered our planet's atmosphere, oceans, and even geology over billions of years. These biological modifications create patterns that would be visible to distant observers, providing a template for what we might look for on other worlds. The most robust biosignatures are atmospheric gases that are produced by life, but would not persist in planetary atmospheres without continuous biological replenishment. On Earth, oxygen represents the classic example of such a biosignature. Our atmosphere contains 21% oxygen, a highly reactive gas that would disappear within millions of years if not constantly replenished by photosynthetic organisms. For a distant astronomer studying Earth's atmosphere, this abundance of oxygen would be a powerful indicator of biological activity. However, the search for oxygen as a biosignature is complicated by the possibility of non-biological oxygen production. Stellar radiation can split water molecules in planetary atmospheres, releasing oxygen that could accumulate to detectable levels without requiring life. This process is most efficient around active red dwarf stars, which emit intense ultraviolet radiation that could create substantial oxygen atmospheres on planets that never hosted life. Distinguishing between biological and non-biological oxygen requires careful analysis of atmospheric composition and stellar properties. Water vapor represents another crucial component in the search for life, though it is an indicator of habitability rather than life itself. Liquid water is essential for all known forms of life, serving as the solvent in which biological chemistry occurs. Detecting water vapor in the atmosphere of a planet orbiting in its star's habitable zone suggests the possible presence of liquid water on the surface, creating conditions where life as we know it could potentially develop and survive. The James Webb Space Telescope has already demonstrated the ability to detect water vapor in exoplanet atmospheres, providing our first direct measurements of this crucial molecule on distant worlds. Webb's observations of K-18b revealed not only water vapor but also carbon dioxide and possibly dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms. While this detection requires confirmation and careful analysis to rule out non-biological sources, it illustrates the potential for current technology to identify possible biosignatures. Methane represents another intriguing potential biosignature, particularly when found in combination with oxygen. On Earth, methane is produced by both biological processes, including bacteria, livestock, and wetlands, and geological processes such as volcanic outgassing. However, methane and oxygen react rapidly with each other in planetary atmospheres, so finding both gases simultaneously suggests active replenishment of at least one of them, potentially by biological processes. The combination of gases in planetary atmospheres provides more robust biosignature evidence than individual molecules alone. The simultaneous presence of oxygen and methane, or oxygen and water vapor, creates what astronomers call atmospheric disequilibrium chemical conditions that require active processes to maintain. On a lifeless planet, atmospheric chemistry would gradually reach equilibrium, with reactive gases combining or breaking down until a stable, inactive state is reached. The persistent disequilibrium that characterizes Earth's atmosphere reflects the constant activity of living organisms beyond individual molecules. The search for life encompasses broader atmospheric and surface characteristics that might indicate biological activity. Seasonal variations in atmospheric composition could reflect biological cycles, such as the growth and decay of vegetation. Spectroscopic evidence for chlorophyll or other photosynthetic pigments might be detectable on planets with substantial plant coverage. Even changes in atmospheric composition over periods of years or decades could indicate active biological processes responding to environmental variations. The search for biosignatures must also account for the incredible diversity of potential life forms and the environments they might inhabit. Life on Earth exists in environments ranging from deep ocean thermal vents to highly acidic hot springs to the upper atmosphere. This remarkable adaptability suggests that life might exist in environments quite different from Earth's surface conditions, potentially producing biosignatures that we haven't yet learned to recognize. Exoplanets around red dwarf stars present particularly interesting targets for biosignature searches. Red dwarfs are the most common type of star in the galaxy, and they have extremely long lifetimes. Many will continue burning for trillions of years, far longer than the current age of the universe. Planets around red dwarfs would have enormous amounts of time for life to develop and evolve, potentially creating highly sophisticated biospheres with complex atmospheric signatures. However, red dwarf planets also face unique challenges for habitability. Many red dwarfs produce intense stellar flares that could strip planetary atmospheres and sterilize surfaces with harmful radiation. The planets closest to red dwarfs, those that might have surface temperatures suitable for liquid water, are likely tidally locked, with one side permanently facing the star and the other in eternal darkness. Understanding whether life could develop and persist under these conditions is crucial for interpreting observations of red dwarf planetary systems. The search for life also extends to the search for technosignatures, indicators of intelligent, technological civilizations rather than simple biological processes. These might include atmospheric pollution from industrial processes, narrowband radio signals, or even megastructures that alter the light curves of host stars. While technosignatures remain highly speculative, the statistical power of current and future exoplanet surveys means that any nearby technological civilizations might be detectable through systematic observations. The development of life detection strategies requires careful consideration of false positives and false negatives. A false positive occurs when a non-biological process produces apparent biosignatures, leading to incorrect conclusions about the presence of life. A false negative occurs when life exists, but doesn't produce detectable signatures, or when our instruments aren't sensitive enough to detect actual biosignatures. Balancing these risks requires sophisticated understanding of both planetary atmospheres and biological processes. Computer models of exoplanet atmospheres play crucial roles in biosignature research, helping scientists understand how different atmospheric compositions would appear in telescopic observations. These models must account for stellar radiation, atmospheric chemistry, surface processes, and potential biological activity to predict what Webb and future telescopes might observe. Comparing model predictions with actual observations helps scientists distinguish between biological and non-biological explanations for atmospheric features. The interpretation of potential biosignatures also requires understanding of planetary formation and evolution processes. The atmospheric composition of a planet reflects not only current processes, but also the entire history of planetary development, including the initial atmospheric composition, the evolution of the host star, and any major impacts or geological events that might have altered atmospheric chemistry. Distinguishing between signatures of past biological activity and ongoing biological processes adds another layer of complexity to biosignature interpretation. Statistical approaches to biosignature detection are becoming increasingly important as the number of known exoplanets grows. Rather than relying on detailed studies of individual planets, astronomers are beginning to look for population-level patterns that might indicate the prevalence of life throughout the galaxy. If biosignatures are detected on multiple planets around different types of stars, this would provide much stronger evidence for the biological interpretation than isolated detections on single worlds. The search for life on exoplanets also benefits from continued studies of life in extreme environments on Earth. Astrobiologists study organisms that survive in conditions of extreme temperature, pressure, acidity, radiation, and chemical composition to understand the limits of biological survival and the range of environments where life might exist. These studies inform our understanding of which exoplanets might be habitable and what types of biosignatures we might expect to find. Future missions specifically designed for biosignature detection will employ multiple complementary techniques to maximize the chances of successful life detection while minimizing the risk of false positives. The planned Habitable Worlds Observatory would systematically survey dozens of potentially habitable planets, looking for statistical patterns in atmospheric composition that might indicate biological activity. By studying multiple worlds simultaneously, such missions could distinguish between common geological processes and the more rare signatures of biological activity. The philosophical implications of successful biosignature detection would be profound, fundamentally altering humanity's understanding of our place in the universe. Discovering that life exists on other worlds would demonstrate that biological processes are not unique to Earth, suggesting that life might be common throughout the cosmos. Conversely, a systematic search that fails to find biosignatures despite examining many apparently habitable worlds might suggest that life is indeed rare, making Earth's biosphere extraordinarily precious. The technical challenges of biosignature detection continue to drive advances in astronomical instrumentation and analysis techniques. The precision required to measure trace gases in exoplanet atmospheres pushes the limits of current technology, requiring innovations in detector sensitivity, optical systems, and data analysis methods. These advances benefit not only exoplanet science but also Earth-based environmental monitoring, medical diagnostics, and other fields that require precise spectroscopic measurements. International collaboration is essential for biosignature research, bringing together expertise in astronomy, planetary science, biology, chemistry, and geology. The interdisciplinary nature of astrobiology requires perspectives from multiple fields to properly interpret observations and avoid the biases that might arise from purely astronomical or purely biological approaches. This collaborative approach also ensures that biosignature research benefits from the broadest possible range of theoretical frameworks and analytical techniques. The search for life on exoplanets also connects to broader questions about the origin and evolution of life itself. Understanding how life develops and spreads in different planetary environments informs our knowledge of biological processes generally. If life is discovered on exoplanets with different conditions than Earth, this would provide new insights into the fundamental requirements and characteristics of living systems. Public engagement in biosignature research reflects the broad human interest in questions about life beyond Earth. The possibility that we might discover evidence for extraterrestrial life within our lifetimes captures public imagination and provides powerful motivation for continued investment in space science and technology. Educational outreach efforts help the public understand both the possibilities and the limitations of current biosignature detection capabilities. As we contemplate the search for biosignatures and its profound implications, there is something deeply moving about humanity's systematic attempt to answer one of our oldest questions: are we alone? The technical sophistication required to analyze atmospheric compositions of planets orbiting other stars represents an extraordinary achievement, yet it is motivated by the same curiosity about life and our place in the cosmos that has driven human inquiry for millennia. The patience required for biosignature research mirrors the timescales on which biological processes operate. Life on Earth developed over billions of years, creating the atmospheric signatures we might hope to detect on other worlds. Our search for these signatures requires similar patience, as we carefully build the technological capabilities and theoretical understanding needed to recognize and interpret signs of life across interstellar distances. In our gentle contemplation of this search for life among the stars, we can find both humility and wonder. Humility in recognizing that life might be rare and precious in the cosmos, making our own biosphere extraordinarily valuable. Wonder at the possibility that we might discover evidence for other living worlds, fundamentally expanding our understanding of life itself and our place in a universe that might be teeming with biological activity we are only just beginning to detect and understand. As we drift deeper into contemplation of our cosmic neighborhood and its 6,000 known worlds, we find ourselves face to face with one of humanity's most profound and enduring questions: are we alone in this vast universe, and what would it mean for our understanding of existence itself if we discovered that we are not? There is something both humbling and exhilarating about the moment in human history when this question transitions from pure philosophy to empirical science. For thousands of years, humans have wondered whether other worlds might harbor life, but only now do we possess the technological capability to search systematically for evidence of biology beyond Earth. This transformation of an ancient philosophical question into a scientific investigation represents one of the most remarkable intellectual achievements in human history. The Drake equation, formulated by astronomer Frank Drake in 1961, provides a framework for thinking about the likelihood of extraterrestrial intelligence. In our galaxy, the equation attempts to estimate the number of communicating civilizations by considering factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction of habitable planets where life develops, and the fraction of life-bearing planets where intelligence and technology arise. When Drake first proposed his equation, most of these factors were completely unknown. We didn't know whether other stars had planets at all, let alone how common habitable worlds might be. The discovery of more than 6,000 exoplanets has filled in several crucial turns in the Drake equation with actual observational data, fundamentally changing our perspective on the probability of life elsewhere in the galaxy. We now know that planets are ubiquitous throughout the galaxy. Nearly every star has at least one planet, and many have multiple worlds. The Kepler mission revealed that Earth-sized planets in the habitable zones of their stars are relatively common, with estimates suggesting that 20 to 50% of Sun-like stars have potentially habitable worlds. These discoveries have dramatically increased the estimated number of potentially life-bearing planets in our galaxy from thousands or millions to billions. Yet despite this abundance of potentially habitable worlds, we have found no confirmed evidence for life beyond Earth. This discrepancy between the apparent abundance of suitable planetary environments and the absence of detected life illustrates what physicist Enrico Fermi identified as a paradox. If the conditions for life are common throughout the galaxy, and if life had billions of years to develop and spread, where is everybody? The Fermi paradox has profound implications for how we understand our place in the cosmos. Several possible solutions have been proposed, each with different philosophical implications. Perhaps life is much rarer than we assume, rising only under very specific conditions that are seldom met even on apparently habitable planets. Perhaps intelligence is exceedingly rare, requiring evolutionary paths that are extremely unlikely even when simple life exists. Another possibility is that technological civilizations tend to destroy themselves relatively quickly after achieving the capability to communicate across interstellar distances. If the typical lifetime of a technological civilization is only thousands or tens of thousands of years, brief compared to cosmic timescales, then few such civilizations would exist at any given time, making contact extremely unlikely despite the eventual development of many civilizations over cosmic history. Alternatively, perhaps advanced civilizations exist but choose not to communicate with less developed species, like ourselves. This zoo hypothesis suggests that we might be deliberately isolated or protected by advanced aliens who prefer to observe us without interference. While this possibility cannot be ruled out entirely, it requires assuming motivations and capabilities for hypothetical aliens that may reflect more about human psychology than about likely alien behavior. The possibility that Earth is truly unique in hosting intelligent life, the rare Earth hypothesis, deserves serious consideration despite our discovery of many potentially habitable exoplanets. While Earth-sized planets in habitable zones appear to be common, the specific combination of factors that enabled complex life to develop on Earth might be extraordinarily unlikely. These factors include our planet's large moon, which stabilizes our axial tilt and creates tides that may have aided early evolution, our location in the galaxy, far from the radiation and gravitational disruptions of the galactic center, the particular history of impacts and geological processes that shaped Earth's atmosphere and surface, and perhaps many other factors we don't yet fully understand. The development of complex life on Earth required several billion years and involved numerous evolutionary innovations that might be extremely unlikely. The transition from simple bacterial life to complex cells with nuclei took over 2 billion years and might represent an extraordinarily rare evolutionary step. The development of multicellular life, sexual reproduction, and eventually intelligence involved additional transitions that each might be improbable enough to make complex life exceedingly rare in the galaxy. From this perspective, the abundance of potentially habitable planets might be misleading. Even if billions of worlds could support life, the probability that any particular world will actually develop life, and then evolve complex organisms and then produce intelligence might be so small that Earth represents a genuinely unique phenomenon in our galaxy. This possibility has profound implications for how we value our own biosphere and our responsibilities as the only known intelligent species. Recent advances in exoplanet science have begun to provide observational tests of some aspects of the rare Earth hypothesis. The James Webb Space Telescope's atmospheric studies are revealing whether potentially habitable planets around nearby stars have managed to retain substantial atmospheres, a prerequisite for surface habitability. Early results suggest that some planets around active red dwarf stars may have lost their atmospheres to stellar radiation, potentially making them uninhabitable despite being located in their star's habitable zones. The search for biosignatures represents our most direct approach to testing whether life exists on other worlds. If atmospheric analysis of potentially habitable exoplanets reveals clear evidence for biological processes, this would demonstrate that life can develop independently in different planetary environments, suggesting that biological processes might be common throughout the cosmos. Conversely, a systematic search that fails to find biosignatures despite examining many apparently suitable worlds might support the rare Earth hypothesis. The philosophical implications of either outcome would be profound. Discovering evidence for life on other worlds would fundamentally alter humanity's understanding of our place in the universe, demonstrating that we are part of a much larger community of living worlds. Such a discovery would likely accelerate efforts to search for intelligence and to develop technologies for interstellar communication and eventually travel. The absence of detectable life on other worlds, despite systematic searches, would carry equally significant philosophical implications. It would suggest that Earth's biosphere is extraordinarily precious, representing a level of complexity and beauty that might be unique in our galaxy, or even in the observable universe. This possibility would place enormous moral responsibility on humanity. As the guardians of the only known flowering of consciousness and intelligence in our cosmic neighborhood, the implications extend beyond questions of biological life to considerations of intelligence and consciousness. Even if simple life proves to be common throughout the galaxy, the development of intelligence, technology, and civilization might be extraordinarily rare. The evolution of human-level intelligence on Earth required specific evolutionary pressures and ecological circumstances that might seldom be replicated elsewhere. The uniqueness of human consciousness, with its capacity for abstract thought, artistic creation, scientific inquiry, and moral reasoning, might represent the rarest phenomenon in the universe. If so, the extinction of human civilization would represent an irreplaceable loss of cosmic significance, eliminating the only known examples of beings capable of contemplating the universe and recognizing beauty, meaning, and value in existence itself. These philosophical considerations connect to practical questions about humanity's future and our responsibilities as a species. If we are alone or nearly alone in the galaxy, then our survival and flourishing becomes a cosmic imperative rather than merely a local concern. The development of sustainable civilization, the preservation of Earth's biosphere, and the eventual spread of human consciousness and culture beyond Earth would represent unique contributions to the cosmos rather than just another example of biological and technological development. The search for extraterrestrial intelligence, through projects like SETI Search for Extraterrestrial Intelligence, represents another approach to testing our cosmic loneliness. Radio telescopes around the world continuously monitor nearby stars for narrowband signals that might indicate technological civilizations. More recently, optical SETI projects search for brief laser pulses that might serve as interstellar communication signals. Despite decades of searching, no confirmed signals from extraterrestrial intelligence have been detected. The absence of detected alien signals might reflect the limitations of our search strategies, rather than the absence of extraterrestrial civilizations. Advanced aliens might use communication technologies that we haven't yet developed or even conceived. They might communicate using quantum entanglement, gravitational waves, or neutrino beams rather than radio waves. Their signals might be so far advanced beyond our current technology that we couldn't recognize them as artificial even if we detected them. Alternatively, the lack of detected signals might support the hypothesis that technological civilizations are indeed rare or short-lived. If the typical technological civilization lasts only thousands of years before extinction or transformation beyond recognition, then the probability of detecting contemporary civilizations becomes vanishingly small even in a galaxy that has hosted many civilizations over cosmic time. The concept of a great filter suggests that there might be evolutionary steps that are so difficult that very few species successfully navigate them. This filter might lie in our past, perhaps the development of life itself, or the evolution of complex cells, or the emergence of intelligence, explaining why we don't observe evidence of other civilizations. Alternatively, the great filter might lie in our future, suggesting that most technological civilizations destroy themselves, or face insurmountable challenges before they can spread throughout their stellar neighborhoods. If the great filter lies ahead of us, this has profound implications for humanity's future. It suggests that we are approaching or will soon encounter challenges that have typically proved insurmountable for technological civilizations. These might include environmental destruction, nuclear war, artificial intelligence risks, or other catastrophic threats that tend to eliminate species shortly after they achieve technological capability. The possibility of multiple great filters adds additional complexity to these considerations. Perhaps life itself is moderately rare, intelligence is very rare, and long-term technological survival is extremely rare, creating a series of bottlenecks that collectively make advanced civilizations extraordinarily uncommon. This multi-filter model could explain both the abundance of potentially habitable planets and the apparent absence of detectable alien civilizations. Recent discussions of the Fermi paradox have also considered the possibility that we are experiencing a great silence, a period during which technological civilizations exist, but are not actively transmitting detectable signals. Advanced civilizations might have outgrown the need for electromagnetic communication, or they might deliberately avoid transmitting signals that could be detected by less advanced species for reasons of security or non-interference. The anthropic principle adds another philosophical dimension to these questions. This principle suggests that we should not be surprised to find ourselves in a universe that appears fine-tuned for the existence of observers, because we could only exist in such a universe to make the observation. Applied to the Fermi paradox, the anthropic principle suggests that we might find ourselves in an apparently empty galaxy, simply because we could only evolve in a galaxy where competitive alien civilizations had not already colonized every habitable world. The implications of these philosophical considerations extend beyond academic speculation to practical questions about human behavior and priorities. If we are alone or nearly alone in the galaxy, then the preservation of human civilization and consciousness becomes a responsibility of cosmic significance. Every effort to reduce existential risks, to develop sustainable technologies, and to ensure the long-term survival of human culture and knowledge contributes to maintaining the universe as only known source of meaning, beauty, and moral value. The exploration of space takes on additional significance. If humanity represents the galaxy's only technological civilization, our expansion beyond Earth would not merely be an adventure or economic opportunity, but a cosmic necessity to ensure that consciousness and intelligence survive and flourish on multiple worlds. The colonization of Mars, the development of space-based civilization, and eventual interstellar travel would represent the universe's best and perhaps only hope for the long-term survival and development of intelligence and culture. These philosophical considerations also affect how we interpret our scientific discoveries and set research priorities. If life is exceedingly rare, then every discovery about exoplanet habitability, atmospheric composition, and potential biosignatures becomes crucially important for understanding our cosmic context. The search for life beyond Earth takes on profound significance, not just for satisfying human curiosity, but for determining our fundamental responsibilities as conscious beings in an apparently unconscious universe. The contemplation of our possible cosmic loneliness can be both sobering and inspiring. Sobering because it suggests that the beauty, creativity, and moral development that characterize human civilization at its best might be unique phenomena that could easily be lost forever. Inspiring because it suggests that every human achievement in art, science, philosophy, and ethical development represents a genuinely precious contribution to the cosmos rather than merely one example among countless others. As we drift peacefully through these profound philosophical contemplations, we can find both humility and purpose in confronting the possibility of our cosmic uniqueness. Whether we are alone or part of a vast community of intelligent beings remains unknown, but either possibility carries profound implications for how we understand our existence and our responsibilities to future generations. The patient search for answers through scientific investigation continues, while the questions themselves remind us of the extraordinary significance of consciousness, intelligence, and moral reasoning in a universe that might otherwise be purely physical and unconscious. In the gentle rhythm of cosmic contemplation, we find ourselves suspended between two equally profound possibilities: that we are alone in a vast, beautiful, but unconscious universe, or that we are part of a community of intelligent beings whose existence we have yet to detect. Either possibility fills our existence with meaning and purpose, whether as unique guardians of consciousness or as participants in a cosmic community of minds exploring and celebrating the wonders of existence itself. As we near the gentle conclusion of our cosmic journey through the realm of 6,000 worlds, let us now weave together all the threads of discovery we have explored, creating a tapestry that reveals the profound transformation in human understanding that exoplanet science has brought to our species. There is something deeply satisfying about reaching this point, where all the individual elements of our exploration, the patient observations of space telescopes, the revolutionary atmospheric studies, the future missions that will search for signs of life, and the profound philosophical implications of our possible cosmic loneliness, begin to form a coherent, beautiful whole that speaks to humanity's expanding understanding of our place among the stars. Our journey began with the remarkable achievement of space-based planet hunting, where missions like Kepler and TESS have revealed that planets are not rare cosmic curiosities, but rather the natural outcome of star formation throughout the galaxy. The patient photometry of these space telescopes, measuring minute changes in stellar brightness with extraordinary precision, has shown us that nearly every star in our galaxy hosts at least one planet, and many host complex systems of multiple worlds in intricate orbital configurations. This statistical revolution has fundamentally altered our cosmic perspective, where previous generations could only wonder whether planets existed around other stars. We now know that our galaxy contains hundreds of billions of worlds, with Earth-sized planets in habitable zones numbering in the billions. The sheer abundance of planets provides the foundation for all subsequent questions about life, intelligence, and our place in the cosmic community. The diversity revealed by these surveys has been equally transformative. The exoplanets discovered by Kepler, TESS, and other missions display a remarkable range of sizes, compositions, and orbital characteristics that far exceeds anything represented in our own solar system. Super-Earths, hot Jupiters, sub-Neptunes, and countless other planetary types have expanded our understanding of what planets can be, challenging and refining our theories of planetary formation and evolution. This diversity connects directly to the atmospheric revolution, enabled by the James Webb Space Telescope and other advanced instruments, where previous generations could only speculate about the atmospheres of distant worlds. Webb has begun to analyze the actual chemical composition of exoplanet atmospheres, revealing the presence of water vapor, carbon dioxide, methane, and other molecules that tell the story of planetary evolution and potentially biological activity. Webb's atmospheric studies have shown us that exoplanets are not merely points of light, but complex, dynamic worlds with their own weather patterns, chemical cycles, and evolutionary histories. The ability to detect and analyze atmospheric compositions represents one of the most remarkable technological achievements in astronomical history. enabling us to study environments that exist trillions of kilometers away with a precision that would have seemed impossible just decades ago. The integration of statistical surveys and atmospheric studies has created a new scientific discipline, exoplanet characterization, that combines the broad perspective of population studies with the detailed analysis of individual worlds. This approach allows scientists to understand both the common patterns that govern planetary system formation and the unique characteristics that make each world distinct. Future missions like the Nancy Grace Roman Space Telescope will extend this integration by combining wide-field surveys with direct imaging capabilities, allowing us to study planets throughout their orbital systems rather than just those that happen to transit in front of their host stars. Roman's gravitational microlensing surveys will reveal planets at Earth-like orbital distances, while its coronagraph technology will demonstrate direct imaging techniques that will be essential for future missions designed to search for biosignatures. The progression from discovery to characterization to the search for life represents a logical evolution in exoplanet science, with each phase building on the achievements of previous efforts. The statistical surveys identified the types of planets that are most common and most likely to be habitable. Atmospheric studies are revealing which of these planets actually possess the atmospheric conditions necessary for life. Future biosignature searches will determine whether any of these potentially habitable worlds actually host biological processes. This progression reflects the broader pattern of scientific discovery, where initial observations reveal new phenomena, detailed studies characterize their properties, and subsequent investigations explore their implications for fundamental questions about nature. In exoplanet science, this pattern has led us from the basic question of whether other planets exist to the profound question of whether we are alone in the universe. The search for biosignatures represents the convergence of multiple scientific disciplines, bringing together astronomy, planetary science, atmospheric physics, biochemistry, and biology to address questions that transcend any single field. This interdisciplinary approach reflects the complexity of the questions being addressed and the need for multiple perspectives to properly interpret observations of distant worlds. The philosophical implications we have explored, particularly the questions raised by the Fermi paradox and the possibility of our cosmic uniqueness, provide context for all exoplanet discoveries. Whether we find evidence for life on other worlds or fail to detect biosignatures, despite systematic searches, the results will fundamentally affect how humanity understands its place in the cosmos and its responsibilities as potentially the only technological civilization in our galactic neighborhood. The international nature of exoplanet research embodies the global significance of the questions being addressed. Scientists from dozens of countries contribute to exoplanet missions, share data freely across national boundaries, and collaborate on theoretical studies that advance our collective understanding. This cooperation demonstrates that the search for other worlds and the possibility of life beyond Earth transcends political divisions and cultural differences. The technological innovations driven by exoplanet research have created benefits that extend far beyond astronomy. Precision photometry techniques developed for transit surveys have applications in medical imaging and materials science. Advanced spectroscopy methods used for atmospheric analysis benefit environmental monitoring and industrial process control. The computational techniques developed to analyze exoplanet data have found applications in artificial intelligence and machine learning research. Educational outreach and public engagement in exoplanet science have inspired new generations of scientists and engineers while fostering scientific literacy in the general population. The discovery that planets are common throughout the galaxy and that some might harbor life captures public imagination and demonstrates the relevance of scientific research to fundamental questions about existence and meaning. The long-term perspective that exoplanet science provides connects individual discoveries to the broader story of cosmic evolution. The planets we observe today formed billions of years ago from the same processes that created our own solar system, yet they have followed diverse evolutionary paths that reveal the range of possible outcomes for planetary development. Understanding this diversity informs our knowledge of how planetary systems form, evolve, and potentially develop conditions suitable for life. The statistical power of exoplanet surveys has enabled studies of planetary demographics that reveal patterns and correlations invisible in small samples. These population studies show how planetary properties depend on stellar characteristics, system architecture, and formation environments, providing insights into the fundamental processes that govern planetary system evolution throughout the galaxy. The precision of modern exoplanet observations has also enabled studies of planetary system dynamics, revealing how multiple planets interact gravitationally over long periods. These studies show that planetary systems are not static collections of worlds but dynamic environments where orbital evolution, tidal interactions, and gravitational resonances shape planetary properties over billions of years. The connection between exoplanet science and the search for life has elevated both fields, providing observational targets for astrobiology research and biological context for astronomical observations. The possibility that some exoplanets might harbor life motivates continued investment in increasingly sophisticated observational capabilities, while astrobiological research on Earth informs our understanding of what types of planets might be habitable and what biosignatures we should search for. Climate modeling has become increasingly important in exoplanet science as we attempt to understand the atmospheric and surface conditions on distant worlds. These models must account for different stellar types, atmospheric compositions, and planetary characteristics to predict whether particular planets might maintain conditions suitable for liquid water and potentially life. The validation of these models through comparison with Webb's atmospheric observations is improving our ability to assess planetary habitability. The synergy between ground-based and space-based observations continues to be crucial. For exoplanet science, space telescopes excel at precise photometry and atmospheric studies, while ground-based instruments provide high-resolution spectroscopy and rapid follow-up observations. The combination of these complementary capabilities enables more comprehensive studies of exoplanet properties than either approach could achieve alone. Machine learning and artificial intelligence techniques are becoming increasingly important for analyzing the vast datasets produced by exoplanet surveys. These computational approaches can identify subtle patterns in data that might be missed by traditional analysis methods, enabling the discovery of smaller planets and the characterization of more complex planetary systems than would be possible through manual analysis. The development of new theoretical frameworks has been essential for interpreting exoplanet observations and placing them in the context of planetary formation and evolution. Models of disk dynamics, planetary migration, atmospheric evolution, and tidal interactions have all been refined and expanded to account for the diversity of observed planetary systems. As we contemplate this integrated picture of exoplanet science, from the initial discoveries that revealed the abundance of planets throughout the galaxy, to the sophisticated atmospheric studies that are beginning to characterize the environments of distant worlds, we can find both practical knowledge and profound beauty in humanity's expanding understanding of our cosmic neighborhood. The gentle persistence of scientific exploration continues to expand our knowledge of planetary systems and our place among them. Each new discovery adds to our understanding of how planets form and evolve, while also contributing to our assessment of the likelihood that life exists elsewhere in the galaxy. The patient accumulation of observations and the careful development of theoretical understanding create a growing foundation of knowledge that will guide future exploration and discovery. The story of exoplanet science also illustrates the power of human curiosity and ingenuity to answer fundamental questions about existence and meaning. The transition from wondering whether other worlds exist to systematically searching for signs of life on those worlds represents one of the most remarkable intellectual achievements in human history, demonstrating our species' capacity to develop technologies and techniques that extend our perception across vast distances and reveal hidden aspects of cosmic reality. In contemplating the integration of all these discoveries and their implications, we find ourselves part of a much larger story of cosmic evolution and development. The planets we study formed from the same stellar processes that created our own world. yet they have followed diverse evolutionary paths that reveal the range of possible outcomes for planetary development. Understanding this diversity deepens our appreciation for both the commonality and the uniqueness of planetary environments throughout the galaxy. The peaceful rhythm of scientific discovery continues day by day, observation by observation, building our understanding of planetary systems and their potential for harboring life. This patient exploration reflects the broader character of human scientific endeavor, the willingness to pursue fundamental questions over decades and centuries, gradually building knowledge that transforms our understanding of ourselves and our place in the cosmos. And so as our peaceful journey through the cosmos of exoplanet discovery draws to its gentle close, let us rest together in contemplation of what it means to be human in an age when we know of 6000 worlds beyond our own, each one a testament to the profound creativity of cosmic processes and the remarkable ingenuity of human scientific exploration. Throughout our exploration together, we have witnessed one of the most remarkable transformations in human understanding, the transition from a species that knew of only the planets in our own solar system to one that has identified thousands of worlds orbiting distant stars, analyzed their atmospheric compositions, and begun the systematic search for signs of life beyond Earth. This transformation represents not merely an expansion of astronomical knowledge, but a fundamental shift in how we understand our place in the universe. The story we have traced, from the patient observations of space telescopes like Kepler and TESS, through the atmospheric revelations of the James Webb Space Telescope to the future missions that will search for biosignatures and directly image distant worlds, reveals the beautiful coherence of scientific discovery. Each mission has built upon the achievements of its predecessors, gradually developing more sophisticated capabilities for studying planetary systems and searching for the conditions that might support life. These 6,000 confirmed exoplanets represent more than statistical achievements or technological demonstrations. Each world is a unique experiment in planetary formation and evolution, shaped by the particular characteristics of its host star, its formation environment, and billions of years of subsequent development. Together they reveal that planetary systems are incredibly diverse, with outcomes ranging from hellish lava worlds orbiting closer to their stars than Mercury orbits our Sun to potentially habitable worlds in the temperate zones where liquid water might flow on planetary surfaces. The diversity we have discovered challenges every assumption we might have made. Based solely on our own solar system, super-Earths, rocky planets larger than Earth but smaller than Neptune, turn out to be among the most common types of planets in the galaxy. Despite being completely absent from our own planetary system, hot Jupiters, gas giants orbiting extremely close to their stars, forced astronomers to completely revise theories of planetary formation and migration. The abundance of sub-Neptune worlds, the discovery of planets orbiting binary stars, and the detection of rogue planets wandering through interstellar space have all expanded our understanding of what planetary systems can become. Yet perhaps even more remarkable than this diversity is the underlying unity revealed by exoplanet science. The same physical processes that formed our own solar system, gravitational collapse, accretion, orbital migration, and atmospheric evolution, have operated throughout the galaxy for billions of years. The laws of physics that govern planetary formation here have shaped the development of worlds around distant stars, creating the cosmic community of which Earth is a part. This recognition of both diversity and unity has profound implications for how we understand our own world and ourselves. Earth is simultaneously typical, one rocky planet among billions in our galaxy, and potentially unique in the particular combination of characteristics that enabled complex life to develop and flourish. The abundance of planets provides countless opportunities for life to arise, yet the specific conditions that led to Earth's biosphere might be extraordinarily rare. The atmospheric studies enabled by the James Webb Space Telescope have begun to reveal which of these thousands of worlds might actually possess the atmospheric conditions necessary for habitability. The detection of water vapor, carbon dioxide, and other molecules in exoplanet atmospheres represents our first direct glimpse into the environmental conditions on distant worlds. transforming abstract statistical knowledge into concrete understanding of actual planetary environments. The possible detection of dimethyl sulfide in the atmosphere of K2-18b illustrates both the promise and the challenges of searching for signs of life beyond Earth. While this molecule is produced exclusively by living organisms on Earth, confirming its presence and ruling out non-biological sources requires careful analysis and independent verification. Yet the very possibility that we might detect biosignatures on distant worlds using current technology demonstrates how far exoplanet science has progressed in just a few decades. The future missions we have contemplated, from the Nancy Grace Roman Space Telescope's comprehensive surveys to the planned Habitable Worlds Observatory's direct search for biosignatures, represent humanity's commitment to answering one of our most fundamental questions: are we alone in the universe? These missions will systematically examine the atmospheres of potentially habitable worlds, searching for the chemical signatures that might indicate biological processes operating on distant planets. The philosophical implications of these searches extend far beyond scientific curiosity to questions about meaning, purpose, and responsibility. If we discover evidence for life on other worlds, it would demonstrate that biological processes can arise independently in different planetary environments, suggesting that life might be common throughout the cosmos. Such a discovery would fundamentally alter humanity's understanding of our place in the universe, revealing us to be part of a much larger community of living worlds. Conversely, a systematic search that fails to find evidence for life despite examining many apparently habitable worlds might suggest that Earth's biosphere is indeed extraordinarily rare and precious. This possibility would place enormous moral responsibility on humanity, as the guardians of what might be the only known flowering of consciousness and intelligence in our cosmic neighborhood. The Fermi paradox, the apparent contradiction between the abundance of potentially habitable planets and the absence of detected extraterrestrial civilizations, adds another layer of complexity to these considerations. Despite discovering thousands of exoplanets and identifying many that might be habitable, we have found no confirmed evidence for technological civilizations beyond Earth. This absence might reflect the rarity of intelligence, the tendency for technological civilizations to destroy themselves, or simply the limitations of our current detection capabilities. The international nature of exoplanet research embodies the global significance of the questions being addressed. Scientists from around the world collaborate on missions, share data freely, and work together to interpret observations that bear on fundamental questions about existence and meaning. This cooperation demonstrates that the search for other worlds and the possibility of life beyond Earth transcends national boundaries and cultural differences, representing a truly human endeavor that benefits from our species' collective knowledge and capabilities. The technological innovations driven by exoplanet research continue to benefit society in unexpected ways. Precision measurement techniques, advanced spectroscopy methods, and sophisticated data analysis algorithms developed for studying distant planets find applications in medical research, environmental monitoring, and numerous other fields. The pursuit of fundamental questions about planetary systems and the possibility of life drives technological development that enhances human capabilities more broadly. Educational outreach in exoplanet science has inspired countless students to pursue careers in science, technology, engineering, and mathematics, while also fostering scientific literacy and critical thinking skills in the general population. The discovery that planets are common throughout the galaxy, and that we might soon detect signs of life on other worlds, captures public imagination and demonstrates the relevance of scientific research to the deepest questions about human existence and cosmic significance. The long-term perspective that exoplanet science provides connects our current discoveries to the broader story of cosmic evolution. The planets we observe today formed from the same stellar processes that created our own world, yet they have followed diverse evolutionary paths over billions of years. Understanding this cosmic perspective helps us appreciate both the commonality of planetary processes and the precious rarity of the particular conditions that enabled Earth's biosphere to develop and flourish. As we contemplate our place among these 6,000 known worlds, with potentially billions more awaiting discovery, we can find both humility and inspiration in recognizing the scope of planetary diversity. Throughout our galaxy, each world represents a unique outcome of cosmic processes, shaped by countless interactions between stellar radiation, atmospheric chemistry, geological activity, and perhaps biological evolution over vast periods of time. The patient, systematic approach that has characterized exoplanet discovery reflects the broader nature of scientific exploration, the willingness to pursue fundamental questions through careful observation and analysis, building understanding gradually over decades and centuries. The space telescopes that have revealed this cosmic community of worlds embody humanity's commitment to expanding knowledge through technological innovation and international cooperation. The story of exoplanet discovery also illustrates the beautiful unpredictability of scientific progress. When the first exoplanet around a sun-like star was discovered in 1995, few could have predicted that within 3 decades we would know of thousands of worlds, be analyzing their atmospheric compositions, and be preparing to search systematically for signs of life. Each discovery has opened new questions and new possibilities for exploration, creating a positive feedback loop that accelerates the pace of scientific discovery. Looking toward the future, we can anticipate that exoplanet science will continue to reveal surprises that challenge our understanding and expand our perspective. The missions now in development will undoubtedly make discoveries that we cannot currently imagine, while also providing answers to questions that have motivated human curiosity for millennia. The search for biosignatures, the characterization of planetary atmospheres, and the quest to understand our cosmic context will continue to drive scientific and technological innovation. In these final moments of our journey together, we can rest in the profound realization that we live in an extraordinary time in human history, an epoch when our species has developed the capability to explore beyond our own planetary boundaries and discover worlds throughout our galaxy. The 6,000 confirmed exoplanets represent not just astronomical objects, but cosmic neighbors in a universe that proves to be far richer and more diverse than previous generations could have imagined. The gentle rhythm of discovery continues, with new worlds being added to our catalog regularly as surveys like TESS systematically examine nearby stars and as follow-up observations confirm the planetary nature of candidate objects. Each new discovery adds to our understanding of planetary system formation and evolution, while also contributing to our assessment of the likelihood that we share the galaxy with other forms of life. Whether we are alone in the cosmos or part of a vast community of living worlds remains to be determined by future observations and discoveries. But regardless of the ultimate answer to that profound question, we can find deep meaning and purpose in being the species that asks such questions and develops the technological capabilities to seek empirical answers across the vast distances of interstellar space. In the peaceful contemplation of our place among 6,000 worlds and counting, we find ourselves part of a cosmic story that connects us to stellar processes throughout the galaxy, and perhaps to other forms of life that we have yet to detect. The patient search for understanding continues, driven by the same curiosity and wonder that has motivated human exploration for millennia, now extended across interstellar distances. Through the remarkable capabilities of our space-based observatories, as we drift toward rest in the knowledge of our cosmic neighborhood's richness and diversity, we can find both comfort and inspiration in being part of a species capable of such remarkable discoveries. The 6,000 worlds we now know are just the beginning of a story of exploration and discovery that will continue for generations to come, gradually revealing the full scope and wonder of our galactic home and our place within its vast community of worlds. Good night from Sleepy Scientist.